Hello. Hello, Majid.
Okay. I'm still trying to check if Robert has joined us, where he's from, but I'll meet later. Okay, and Melis we have. Good morning, Melis. Marena, you might be at your computer now. Good morning, Marena.
Good
morning. Good morning. Good morning, Reinhard. Okay, and good morning, Kubra. Okay. Let me just check. Okay, Majid, do you think we should maybe start? I don't want to let people wait for too long.
Yes, we can start, Professor.
Will it be okay? Okay, Aaron, is Majid not in his office at the moment?
Yes.
Is he not there? Okay, so maybe it's okay. Okay, if we start, I'll just open where's my file? I'll just try and find my file in the meantime. Sorry, I've got too many things open here. There we go. I'm just not sure. Oh, no. Sorry, no, that's the wrong file. Let's this one. Okay. Get this out of the way again. There we go. Okay, good morning, everybody. If it use all the languages, it would be goeiemorgen in Afrikaans, good morning, good night, and buenos dias, molweni would be isiXhosa. So good morning, everybody. Welcome back to today's training. Again, as we did yesterday, I will do this morning session and Prof. Rosario will do the afternoon, continuing with chemometrics. I didn't complete the introduction to chemometrics yesterday, the slides that were in that I had, but Rosario actually covered majority of that yesterday afternoon. I might have explained it in a slightly easier way, or maybe more for people who's really not familiar with chemometrics, but Rosario really explained it in a way that I'm sure it was understandable, even for people who've not been dealt with chemometrics before. So I think what I'll do this morning, I've actually got 4 topics that I would like to cover. My slides might contain more information, which is probably not relevant and necessary to cover in detail today. So I might skip some slides, but it would not mean that I'm actually skipping important information. It might be because my slides focus quite a lot on serials, since I mostly work on serials. I don't think we really need to cover the details on all the serial applications in detail. So I will, where it's actually relevant, where it could be relevant to other commodities as well, I will highlight that and I will mention it. Otherwise, I might skip some slides. So I just want to mention that I've decided in advance that some slides might not be 100% applicable. So I'm going to start off with covering some information, just a little bit on instrumentation. So just to introduce you to the instrumentation. Again, I'm focusing on the application and the implementation and not as much on the physics and optics of the instrumentation. That could be a session for a different time if necessary. So I'm going to cover instrumentation. I'll have a very short presentation on reference methods. Then I'll cover a few factors that can typically affect the quality of your calibration and of your analysis. And then if there's time, I will just highlight a few applications where NIR is typically used. So although I tend to use the term instruments mostly in this presentation, NIR instruments, or it's an analytical instrument, and it's typically referred to as spectrophotometers or spectrometers. A lot of people find spectrophotometers a real tongue twister, so it's maybe easier to use spectrometers, or it's an analytical instrument. So instrument is also okay to use. Just one thing, it's not a machine. There's no gears involved. So please don't call our spectrophotometers machines. It's not machines. And the instruments that we work with, all the spectrophotometers, can be used inline, online, at line. So it can be online where continuous measurements are done. So then a number of things like sample presentation, sample collection, sample preparation is not really valid. Also, collecting a sample is not valid because you continuously analyze all the samples. For this presentation, we will mostly focus at line instruments or standalone instruments. So that would be an instrument that's situated on a bench top. You need to collect a sample and analyze the sample. So yeah, as I said, inline instruments analyze online. You basically analyze just about all the sample or all the material. But in the case of at-line or standalone instruments, you need to collect the sample and present it to the instrument. And those two actions are really important, and I will probably refer to that a few more times. So firstly, the two types of instruments we get. Some instruments work solely in reflectance mode, so you only get reflectance spectra, which we again report as absorbance, and instruments that work in transmittance mode. So in both cases, we have the light source, we have the wavelength selection system, whether it's a monochromator or interferometer. In the older days, and sometimes still some instruments only work with a few dedicated filters, so that would be the filter system. And then in the case of reflectance, the light penetrates the sample and it's reflected back off the sample, or it penetrates the sample, passes through the sample, light is absorbed and remaining light is reflected at the other end. So the reflector is at the other end, the detector is at the other end of the sample. So we can do measurements either in reflectance or transmittance, and I will refer back to that a few more times. The difference between reflectance and transmittance would be the thickness of the sample. In the case of reflectance, it's important, we almost refer to it as you need the infinite thickness. So most important, the light should not be able to go through the sample. So it should be able to penetrate to whatever level. Normally it's not more than 1 to 2 millimeters. And then the light that's not absorbed is reflected back to the detectors. When we work in transmittance, this is often in the case of grains, would be whole grains. The larger the grain, the thicker the sample thickness would be. Because of the large grains, there will be large openings between the samples. So there's a likelihood that you might lose some of your light energy. So you will have a thicker sample thickness to make sure that you collect as much information as possible. When you work with flour, can also be analyzed in transmittance, then your sample thickness should not be more than about 3 millimeters. And then similarly, liquids would also be done in transmittance. But I will show a few examples what can happen and the thickness of your cell or your cuvettes when you analyze liquid samples. So the thickness of the sample is important depending on whether you use transmittance or reflectance systems, and also for the type of sample. And also, I just want to mention, so some instruments that work in transmittance mode typically scans between 780 and 1098 nanometers. The reflectance instruments can easily work from 400 to 2500. However, the information that we can typically use best is from 700 upwards, or in most cases, you will see reflectance instruments only work from 1100 to 2500. Or again, if in-gas detectors are used, they only work up to 1700. So there are actually some reflectance instruments that only operate up to 1700. But again, as we saw yesterday, we work with combination bands and first, second, third overtones. Even if you scan up to 1700, you still tend to include all the information, specifically the chemical bonds that would assist you to do your quantitative predictions. Just to show the difference between, for example, a whole grain, so a larger sample, compare sample size, the grain size compared to a ground sample. So we see in the case of the whole grain, the intensity of the energy that reached the detector is much less than in the case of the ground sample. And this is also because you get more scattering of the grain kernels, and also the difference between, so the light needs to penetrate the sample where there's difference between the bran and the endosperm. So less energy is observed or obtained, and also more scattering. And that we can see, as we discussed yesterday, in the large baseline shift between the different samples here, or the whole grain samples, compared to the ground samples. So the more particles of the flour also contributed to the better efficiency of the diffuse reflectance analysis. This is just, I just thought to show this as well. This is these are two scans of sunflowers, the whole sunflower and the ground sunflower. Sunflower contain oil content of between 20 and 50%. So you would expect, remember I showed the plot yesterday of pure oil, where you could clearly see. I just want to check, we've got, somebody's got their mic on. Okay, there we go. Sorry, just want to go back. Yes, so as do you remember the oil spectra that I showed yesterday, where we could clearly see the oil peaks around 2300 and around 1700 here. So in the case where we scan the whole grain sunflower oil, the oil peaks are not present at all. And this is because of the thickness of the seed coat. So it's really difficult for the NIR light to penetrate through that thick seed coat to actually reach the area where the oil is present in the kernel. So as soon as we ground the samples, the oil peaks became really prominent. We can clearly see the oil peaks. So similarly, if we do the second derivative, which we learned yesterday, can help to split these overlapping bands. So in the case of the ground sunflower, we can clearly see the oil peaks around 2300, where in the case of the whole grain sample, they're just not visible at all. So how you present your sample, in which form you present your sample, will definitely affect the quality of your calibrations that you develop, or whether it would actually be possible at all. There are different systems of wavelength selection for different instruments. I'm not going to go into detail of this. Initially, it was discrete filters where the work, say 5 filters was selected, 2 where we know protein would absorb, 2 absorbance wavelengths where we would know moisture would absorb, and maybe a couple of wavelengths which were independent, that none of the chemical compounds would absorb, like reference spectra of reference wavelengths. And you could actually by only using those 5 filters, predict moisture and protein quite effectively in, for example, grain samples. So this is how it all started. And nowadays, even if you still want an instrument only to be used for dedicated predictions, you can still just use the instrument with discrete filters. but mostly nowadays we use instruments with grating monochromators or interferometers that allows you to scan the entire wavelength range with, say, maybe every second nanometers. Some will scan every 5 or 6 nanometers, but most is about every second nanometers. I just want to show examples of a few instruments. So this, the Bruker, similar to the Buchi instrument, is typically, it's used in industry, but this would be the instruments that you would typically see in a research environment, because it enables you to scan flower samples, whole grain samples. You can do liquid samples in transmission with a automatic sampler. It would have fiber optic probes where you can do interactance measurements direct into the sample. So this really enables offline transmission, reflectance, also transflection. I will actually ask Typhoon. Typhoon, if you're next door, you can maybe just come and show us your Petri dish with the transflectance plate. I will show you that to you at some point, just to show how one can do transflectance measurements. So typical research instrument, but also used in industry. The Matrix F, also a Bruker instrument. This was the instrument that they've installed in those minivans initially when they needed a portable instrument. Here again, offline transmission, transflectance. It also has a fiber optic probe and also a contactless measure head. So there's a measure head here, which is not in contact with the sample. The Metrome analyzer, if I remember correctly, this runs the entire wavelength range, 400 to 2500, and also quite applicable for solids, creams, liquids, almost covering the entire production chain, any type of application that you would like to do. The Buchi NIR-Flex, which you have here at Metu, we also have this at Stellenbosch. Here you can do, you can just fill a Petri dish with your sample. You can do, in this case, it would be reflectance analysis, where the light beam is at the bottom of the Petri dish. You can also, instead of the Petri dish, they have a sample holder where you can scan tablets, where you can hold different sizes of tablets. Honey ran into problems where some of his tablets were actually too big for that specific fitting. So he needs to find a solution for that. Also, this entire unit in front can be removed and replaced with a new unit where you can do liquids in cuvettes. So you can cuvettes with different path lengths, or you can use the Petri dish with a transflectance cover, which you would put on top of it. So the light beam will go in, hit the transflectance cover, and go back through the sample again. So you almost get like double the actual path length. This instrument, it's a Buchi instrument. It's interesting because it's made from food grade stainless steel. So this is really useful to use in the factory. And similarly, this instrument contains IP65 strength glass, so also safe to use in factories. So they have very hygienic designs, and either one of them can actually be, I think it's this one, can be cleaned with water jet cleaning. So you can really just clean it with a spray of water. So these are specifically designed for industry application. This instrument is specifically for moisture oil grains in oilseeds. So it's really a dedicated instrument. It can be carried around. You can measure wherever you want. And this is really designed, it will have factory calibrations developed from huge data sets where you can measure very specific commodities and properties. What one see nowadays, I'm just sort of digressing a bit, what one see nowadays in research is a lot of people will do research covering for a certain application, covering the entire wavelength range. But the last bit of the paper will always, they will spend time on using the beta coefficients, or very important, specifically using the beta coefficients, for example. And then they will determine which wavelengths are the most important. And similar as Rosario showed yesterday with the loading line plot. So you can really see which wavelengths contribute to certain classes or certain separations in a PCA plot, for example. Then one can use, so the idea is of those research is to then develop an instrument only using those wavelengths to build an instrument such as this, which would be cheaper than the normal scanning instruments. And then obviously, as I showed yesterday, there's actually a huge range of handheld instruments. And the fact that they quite affordable, the Harvey is quite expensive. It's not as cheap. I think it's over to close to 300,000 Rand. So it is quite expensive, but many of the other handheld devices, especially the miniature devices, are not that expensive. And it was really interesting. I just checked how these devices are used in research nowadays. So I just did a search quickly on Web of Science, and I found that if you search for handheld or portable devices, in the last 3 years, I found about 30 research papers. And when I search for miniature devices, applications of miniature devices, there in the last couple of years, there were about 60 papers published. So it really is for people who would like to do an application and keen to publish a paper and publish their work. It's amazing how these miniature devices has given a lot of people the opportunity to do NIR work, where in the past, because they couldn't have, if it's not a large or a laboratory instrument, desktop instrument is not affordable, these small miniature devices give one the opportunity to also do some test NIR applications and do NIR work. So when you actually select an instrument, there's a huge list of things that you need to look at. And I'll just highlight a few important ones. I've now mentioned a number of different instruments, whether you can do reflectants, powders, liquids. So depending on your application, you will specifically look for an instrument that's most suitable. So you need to find something, if you only want to do whole grain, then you can go for a shorter wavelength, 780 to 100, 1100 instrument that can only do whole grain, which will be more affordable. So you really have to look at your application. Something else that's important would be calibration transferability. So if you have a facility where you need instruments at a number of factories, you will make sure that your calibrations can be well transferred between the different instruments. Spectral quality, instrument durability is important. It's slightly out of your hands, but you will really look for instruments that can guarantee you good spectral quality. You can decide whether you just want an instrument such as this, no computer, no keyboards, or whether you really want more control, where you want a keyboard and a computer connected to it as well. Then something that's always really important when we work with NIR instruments, not just support in terms of the instrument, but also support in terms of training how to use the software that's dedicated to the instrument. That is important. And then finally, if you want to do like a network of instruments that goes together with the calibration transferability, you have to make sure that that support would be there from the company as well. Yeah, so probably the main question is, do you really need an NIR instrument? But if you do day-to-day analysis, loads and loads of analysis that are really costly, and that if you don't have those results will cost your money, your company money, then it definitely is something to consider. And again, as I said, depending on the application, if it's wheat flour, you might get away with you might get away with the dedicated whole grain. If it comes to feed formulations, food product formulations, then it becomes more complicated, and you might need a scanning instrument that would really can handle much more variation and differences. I thought to just include this just to show you quickly how one should not necessarily be worried about the cost of the instrument. This is a calculation that Phil did for 2 instruments. So he worked out that if your instrument costs 30,000 Rand and you say you want to pay it off over 10 years and you analyze 50 samples per day, then that sample only costs you about 20 Turkish lira per day. And if you have a more expensive instrument, also want to pay it off over 10 years, then your actual sort of cost per sample per day, if you do 50 samples, would be what, about 30 Turkish lira or 30 South African Rand. So it's it really is efficient in the end. And as we've seen, these devices really last for a long period of time. So it's not that you'll have to replace your instrument regularly. So in the end, it really does make economical sense. The most important thing when it comes to NIR work is the representative sample or a well-prepared sample. And maybe I haven't really discussed this in detail, is we mentioned that NIR instruments are secondary instruments. You cannot use the instrument as is. So we have to calibrate the instrument. And typically, because we analyze the entire sample, it's not a sample that you extract the nitrogen which you measure. Whether you want to measure moisture or protein or starch or sugars, anything you want to measure, ascorbic acid, you measure the entire sample. Therefore, when we calibrate the instruments, we calibrate with a real sample. So if you want to measure something in chocolate, you don't make an extraction and measure that, you measure the entire piece of chocolate or the entire spread. Or if you want to measure Turkish delight, you don't extract something from the Turkish delight, you measure the entire block of Turkish delight. And because of that, we have to collect samples and prepare samples. And that collection of samples is really important. And typically, if you work in a factory or in the grain industry, you will have bulks and bulks of wheat, but you have to sample it. So how to collect a proper representative sample from that bulk, that is important. If you have the factory that produces a huge number of samples every day, you have to find a way to make sure that you collect representative samples during that day. That will really provide you with a valid answer or a valid data set. So the sample, selecting a sample, make sure it's a representative sample, and also that the set of samples that you collect to develop your calibration should be similar to the samples that you would like to predict in future. Because remember, you develop a calibration to use it again. So the samples in your calibration and the ones that you want to predict should be similar. And so I'm going to spend a little bit of time on sampling. So sampling, it's important that it's affected by the homogeneity of the population, where you take your sample, how you take your sample, how often you take your sample. And again, people would present courses of 2-3 days on sampling. So we don't have time to do that. So I just want to stress the importance of sampling, and knowing your commodity, you would know how to sample. So in this case, it's like bales of hay. They did manual sampling, but they made sure that they sample right through the bale of hay with this, or straw with this probe that they use. Here is a stream of wheat. It's a really old picture, but it just shows how you can efficiently sample. He had a piece of wood with a can on top of it. And just as the wheat is delivered, just regularly taking subsamples, which are then afterwards thoroughly blended, would give you a good representative sample. So there's different ways and means of selecting samples. There are automatic ways of selecting samples. Sample selection, obviously, also very important when you do your reference methods. This is, some of you might be familiar with this, the Boone divider. So if you have a larger wheat sample or cereal sample in your laboratory and you want to get a representative sample, you basically pour the wheat in, it rotates in the divider and it splits it in 2 samples. If you want a smaller sample, you empty the one, pour it back in and split that sample again. So you can continue splitting until you have a smaller sample. And I once attended a sampling course, and one of the experts in sampling was visiting Stellenbosch. And at that time, these discs was really popular to use in wine bottles to make sure that the bottle doesn't trip once after you've poured the wine. And he actually just took one of these discs, and if you fold it in double and you have a powder, a large amount of powder, these little discs are perfect to just scoop up a representative sample from a powder population. So you can find different ways of means to innovative ways to do effective and representative sampling. Yes, and also, especially in terms of wheat, you often need to grind the sample. And if you have to grind the sample, then there's a number of things that you have to look at. So you can use different molds. Okay, let me just check what do we have here. Yeah, this is just what I've just said. Okay, let me go back to grinding. Grinding, then it's important to use a mold that will result in least moisture reductions. You don't want the sample to heat up while you're grinding. And typically, because the particle size affect your sample and your spectra, you would tend to use the same grinders for the same application. If you change the grinders, it will definitely affect your calibration. A couple of things to remember, and I know some of it is really basic, but so important. Careful labeling. Okay, labeling. If you can't match up your spectra with your reference methods, then it's a disaster. Accurate subsampling. When you sample for scanning, make sure that your sample is properly stirred, properly blended. And then because we can store wheat quite easily, we tend to store a lot of samples, but even samples that can store easily and can store well, you have to make sure that it's properly done. Yeah, we discussed size reduction. So when you do grinding, important to use a grinder that's efficient and effective for your commodity, and also the same grinder for the same application. Oh, okay. And then when you present your sample to the instrument, this is important. It always needs to be done in a consistent way. So if we have a Petri dish, if you fill it with powder, you would tend to scrape it off. You would probably sort of just from a 2 centimeter distance, drop it once on the bench top, just so that it's settled, but you would always do that in a consistent way. What some of the instrument manufacturers who work with whole grain, they try to get that you to sample and to present your sample in a more consistent way. So maybe I can just show you these 2 short videos. These are 3 whole grain devices where you basically pour in the sample at the top. So the sample is poured in here, on the top there, and there you can see there's a drawer at the top where you will collect the sample afterwards. Some of these devices, there's 2 things. The one thing is they have a little hopper system inside. So the sample is poured in, then it has a little hopper system that allows a small amount of sample in, it's scanned a second amount. So you actually do subsampling while scanning. So when we do reflectance measurements, the Petri dish rotates and you do subsampling as the Petri dish rotates. Some of the instruments has a long glass cell. As it moves down, it scans. So you do subsampling. These ones have like a hopper system inside. And also because all of the grain drops down at the bottom in the drawer, what they've done with some of these devices, they built in a little scale or a balance. So once the sample is dropped through and it's the exact amount of sample that it weighs, it can actually calculate the hectoliter mass. So it calculates the density of a certain volume of wheat, which gives you the hectoliter weight. But let me see if I can just open 1 or 2 of these.
Reinvent your hiring with tech.
Sorry, I'll get past it. I missed it again. Let me do it again. Okay, there you see the wheat is poured into the hopper at the top.
No, Marena.
Sorry, can you see the video?
No.
You
No.
can't see it. Oh, my screen share is paused. Sorry. Let me just, why is it paused? Shall I just stop share and share again? Sorry. Let me just share again. I thought this might happen. Let's go back here. Okay, I'll just show it again. Can you see it now?
Yes,
Sorry.
we can see it.
You can see it now. Okay, there we go. Okay, so that's just poured in, and because it doesn't fall right through, so the distance from where you pour does not really have such a big effect. So it scans. And there you can see, as I said yesterday, it's one scan and you get 1, 2, 3, 4, 5 pieces of information. So this instrument also can measure hectoliter mass. So it weighed, it calculated the hectoliter mass, predicted protein, moisture, predicted gluten content, also Zeleny index, which is an indicator of bread quality, how well that wheat or flour will be able to bake a piece of bread. So really easy, you have your sample ID, sample number, and you have your little receipt of your prediction. Really easy way of measuring, and the sample collected in a tray. Okay, so I'll just go back to, I'll just stop share. Sorry, let me just find, oh no, it's the same, I can come back.
You might have seen videos like this before.
Okay, I just need to share again. Where's my device now? This one.
It's the big secret. Anyone can make one of these videos in a few minutes.
I just want to make sure you can see it now, Rosario. Can you see the monitor? Can you see the video?
Yes, the first video.
First video, yes. Okay. So there's no sound on this one. So this is just a drawing. So filling the sample again. What one would tend to do to make sure it's consistent, you will always fill almost like a similar amount, not just exactly enough, but a similar volume of grain. It presses the button, and in this case, there was a protein content, moisture, starch, wet gluten, Zeleny, and I'm not sure what the W in this case is. So there's no hectoliter mass in this one, but a series of analysis. Sorry, I just want to. Sorry, it's people active in the lab. Okay, let's continue. Okay, and the sample is collected again in the tray at the bottom. And this will now show how it does the subsampling. So the sample is filled from the bottom onto this little conveyor belt. Then you see it's filled, just taking one subsample, it's scanned and dropped. Another subsample is filled, scanned and dropped. So these devices actually have a built-in method, a built-in way of doing effective subsamples from a larger sample. I just thought that was just...
Wait, the 10-gram sample accurately to the second decimal.
Oh, am I now still... Can I just close this? Sorry, was that my video speaking? Yes, okay. Okay, let's continue. So most instruments use some sort of sample cell. So you could see now these hoppers, but there would be a glass through which the scan is done. So there's always some sort of sample cell, and these cells typically are made of glass, and that could have an effect on your calibration. And similarly, liquids are scanned through throw-through cells also made from glass. So the one thing I want to get to, I'll get back to the glass in a minute. Fiber optics are often used. They're really handy because especially for raw ingredients, you can just press it into your sample. The main important thing with fiber optics is the longer the cable, the less efficient it becomes in the longer wavelength ranges. But fiber optics is a really effective way of scanning, especially in factories. Okay, then coming back to the windows. The windows are often made of glass or quartz. If you use a Petri dish, it's typically a glass Petri dish. The cuvettes are typically made of quartz, and sometimes in the instruments they also use quartz. And what we see is, you often see, this is a difference between glass and quartz, but now I just have to say this is second derivatives. If you look at the scale, it is really small differences, so it's really exaggerated here. And similarly, you also see differences between two quartz windows. And similarly would be the case if you use two glass Petri dishes, there will be a difference between the Petri dishes. But you cannot now, when you calibrate, only use one Petri dish. So I'll just show quickly here where they've scanned, they developed a calibration with one glass window and predicted with the same, or developed a calibration with one glass window and then predicted it with the second glass window. So when they predicted with the same, RPD was 21, with the second one 19. Or with the quartz, it was 19, the second one was 18. So there's a slight reduction in the accuracy of the model. So what is important here when you have different quartz or glass windows or different Petri dishes is you cannot use only one. If you only use one and it breaks, then your calibration does not work anymore. So the best thing would be is if you have 10, if you develop a calibration, you have 10 Petri dishes, is to use all of those Petri dishes for your calibration. So you don't have to scan every sample in all the Petri dishes. You would just use all of the Petri dishes in the course of scanning your sample. And this is almost like built-in variation. So next time when you predict, when you develop calibration, that variation is included and it would not affect your accuracy of your calibration. So if you scan both windows and combine them in your calibration, your bias that you might get would be eliminated. So just important in terms of sample presentation that you keep that in mind. This is just a few spectra where water was scanned at different path lengths. So this one was 0.2 millimeter, 0.5 millimeter, 1 milliliter, 2 and 10. This one was 10. So you can see the 2 and 10 millimeters, it's just spectra. The the detectors were completely saturated, you just won't be able to use those spectra. But even if we look at the bottom three, a 1 millimeter path length also still seems to be too long for to scan water or liquids. So you have to be careful when you start scanning liquids to make sure that you use the right path length. I know it's really tedious to work with a 0.2 or 0.5 millimeter cuvette. How they actually make the cuvettes, it's not like a little container, it's actually two pieces of glass, which you just, with a little indent, which you fill with water, close it with a second glass, and then you put it in a cuvette holder. So it's important when you scan quartz cells with different path lengths in transmittance to check that your path lengths would not be too long. Just something on storage of samples. If your sample can be stored, as always, this is something that you would know from any analytical work that you do, is that your samples should be stored properly dated, and make sure that your label might not rub off on the outside of the sample. So make sure that you won't use your label at some point. So grains we can fortunately store for long periods of time at refrigerated temperatures. Freezing is not always advised because sometimes can change the physical characteristics, but important to store. Something else that I actually just thought of this morning is, because NIR is non-destructive, this is really one of the few methods where you can actually scan a sample and then you can analyze that exact sample. So you really can get a reference method of that exact sample if you don't need that sample for any other analysis. So it is really a great way to then develop accurate calibrations. Check cells is important to check the working of your instrument every day. Some of the instruments comes with a closed check cell. So this is a cell that contains some or other powder or flour. You know the content that flour should be able to predict, and you measure it every day and check it every day. So this really is an easy way to indicate the working of your instrument and that it's actually still working efficiently. This is over and above the diagnostics that you can do within the instrument itself. Just something about calibration transfer. This is something that if you need to do that, that's something that because when we do research with NIR, we don't necessarily think about calibration transfer. But if you work in industry where you have to use calibrations at different instruments, it is important to discuss this with your supplier, that you would be able to transfer calibrations, whether the calibration is developed with dedicated software or whether the calibration might have been developed in Unscrambler or MATLAB or wherever. So you have to make sure that that transfer would be possible. Okay, I think, yeah, this just repeats the different ranges for the different.
مش شرط يعني لازم، هي المهم انه بعدت عن your MDL، بعدت عن MDL. بس اذا انا بدي راجعها تعطيني same result as بدون ما نكون عاملها concentration. معناها كيف كانت النتيجة؟ هي منيحة هيدي لما تكبري الفوليوم لما يكون شيء ابدا، يعني يطلع لك كانك ما عم تقري، كانه بلاك. هلا برجع بشوف ايش كيف كان تقرا معنا وقتاش
We can wait for Marena again. Some minutes.
My apologies, all my computer cable wasn't plugged in properly and it just died on me. Okay, but I'm close to the end of this session or this presentation. Oh, do I now need to sign in? Sorry. Can you hear me or do I need to sign in?
Yes, Marena, we can hear you.
Okay, you can hear me, so I just need to share my screen. Thank you, Rosario. Or if I now shared the wrong screen. Okay, let's see. There we go. Oh, my screen is sharing. Sorry, my screen is sharing. There we go. Okay, so I just want to conclude on storage, the importance of storing sample properly, and that everybody knows who works in analytical chemistry, the importance of that. And then the last thing was calibration transfer. If you need calibration transfer, that is something that you really need to discuss with the suppliers to make sure that that would be possible. And similarly, transferability of calibrations between different instruments at different locations. Even when your calibrations are developed at factories, then it's important that you monitor the quality of those calibrations. Okay, this we've covered. And this was just an interesting application. It's just interesting sometimes to look at these things. So Phil did an application where he looked at fiber in animal feed. And by looking at different wavelength selections, he actually found in this specific case, using the entire wavelength range resulted in the best prediction. So it was the entire wavelength range. And nowadays, there are different means in chemometrics to effectively determine which wavelengths, and sometimes specific wavelengths, are more efficient for certain applications, and we often see people doing that now to a great extent. Spectral quality obviously is important. That means you don't want any noise, you don't want any abnormalities, and to some extent we rely on the suppliers to provide us with instruments with less noise, but it can be that certain samples cannot be analyzed effectively over an entire wavelength range. So this is just, for example, if you look in detail, if you do a second derivative, this is scanning a wheat sample at a low, this is within the visible. You see how noisy these spectra are. So scanning wheat samples in the visible range is not really necessarily, might not be as effective. Similarly, this was straw that was packed in a cell, but in this case, it was not loaded, and it was not loaded evenly in the cell. So the sample wasn't packed in the same way each time. And here again, we see anomalies in the spectra. So that's why it's important, once you scan sample, always to look at the quality of your spectra. So just to summarize, sample presentation is important. Use a reliable laboratory for your reference methods, that's important. Check samples to make sure that your instrument still performs the same every day. Factory calibrations needs to be checked that it actually performs accurately on your commodity or your samples. So you need a reliable monitoring system. It's important, although it seems like an easy analysis to perform, you just pour the sample into the instrument, your operator still needs to be thoroughly trained to operate the instruments. And then the diagnostics, which is something that's done just within the instrument. If you have a check sample, you may do that every day, but the diagnostics should be run at least on a weekly basis to make sure that the instrument inherently still performs the same. Okay, so that's was just a brief session on instrumentation. I think before we take a break, if you don't mind, I'm just going to run through a short presentation on reference methods. I just need to find them. Just a couple of things that one needs to keep in mind when you... Okay, reference methods, reference analysis. If we do quantitative work, then reference methods is really important. So that we cannot get away with that. So spectra is important. We need really good quality spectra. That's the heart of the NIRS technology, the heart of the spectroscopy. But if you want to apply NIRS, the reference test is really important. So if you don't have spectra, you cannot do it. You cannot scan anything. You don't have a technology. But if you don't have these reference tests, there's just no option of developing an application. So your reference test would be any property against which the spectral data is requested to develop a calibration. So the calibrations that, the way that Rosario showed yesterday, chemometrics, transformation, pre-processing, doing calibrations, that can be done if you have spectra and reference results that match those spectra. It doesn't matter what it is. And if you go through the applications, I think there are very few things that people haven't tried. There's, you can, if you think of a new application and you go and Google it, there's most likely somebody who's tried that already. So, and the properties could be constituents, which is normally easy. So that's protein, moisture, oil, starch, something that's present at a certain percentage. That's usually easy, and that one can usually do at a reasonable accuracy, providing those compounds contain NH, NO, SH, something that H or a bond that absorbs in the NIR range. But we've seen that we can also predict functionality. you can see like kernel texture, as we showed, because of the scattering properties. People found that they can predict sensory properties, germination potential, because you don't actually measure germination as such, but germination release of enzymes. You change the water levels. So by measuring something that it's actually related to allows you to make that measurement. Something that's interesting is sodium chloride does not absorb in the NIR region, but they can measure sodium chloride, for example, in butter. And what happens is they've noticed that the presence of the sodium chloride somehow affects the moisture band. So you might get a slight shift in the moisture band. And when you do the calibration, the instrument and the software picks that change, which is different for different levels of sodium chloride, up as a valid change, and then calibrate against that, and indirectly you can predict sodium chloride. Similarly, you can predict minerals in soil, which theoretically you should not be able to do, but potentially because of association with other compounds, it is possible. So it's possible to really measure just about everything. Every now and then you start something which you realize just cannot be done, and then you just have to accept that. In the case of reference methods, one tends to use approved methods because they're approved, they're usually run by accredited laboratories, so you should be able to rely on those measurements. If that's not available, you could have your own methods as well, which should be well written up. So there are also in serial science, there's approved methods, but we also have the AOAC, the AOCS, the brewing chemists have their own methods, ICC have their own methods. So there really are a range of approved methods, and if not approved laboratories that would have reliable accredited methods, or often being researchers, we will probably do our work ourselves and then ideally use an approved method. Because there are many things that can differ between laboratories doing even the same method, it is really important to check that your samples is analyzed correctly. And so a lot of people, if a company has different laboratories, they will often do interlaboratory tests to check the interlaboratory reproducibility. So they would do ring tests. So say in South Africa, there's a number of laboratories doing serial tests. So one of the Southern Africa Grain Laboratory would set up a series of ring tests, and they would send the same sample to all of the laboratories, and they will analyze the sample. They will analyze the samples, and the data will be analyzed to see how these different laboratories differ or compare. When you send your own samples for analysis, it's always a good idea to send in blind duplicates. So you will send in the same couple of samples more than once, but with a different label. So that would also give you an idea of the reproducibility of the laboratory if you have your samples analyzed elsewhere. So it's important to do that. You might even do that yourself. You can ask, when you do your own analysis, ask a friend to add a duplicate sample which you don't know what it is, to see if your samples is reliable. And this was just some collaborative tests, and it's easy to see that, for example, moisture was easier to do reproducible than, for example, ash. So not all samples not all tests are as easily reproducible by different laboratories and different people. So there will always be some level of deviation when you have reference tests done by other people. And one can, I'm not going to go through all of this in detail, but this just gives you an indication when you do a lab or a wet chemistry test, how many things can affect your test. This is just a plain protein combustion analysis. It's done on really, really small samples. So the sampling and that sample size already can have an effect on your analysis. How well you've blended, and then everything that's involved, how well you did the prepared the pellet, the gases that's been used, whether you did your moisture correction correctly, how well you maintain your instrument. There are always a range of things that can affect your measurements. So you really just have to attempt to minimize these as much as possible. Moisture, easily just from grinding the sample to actually doing the test, you can already start using moisture. Ash analysis also, you might have moisture uptake in the desiccator. You can get moisture uptake during weighing. So you have to work really quickly. Your ashing might not have been complete. Again, a range of measurements that could have, a range of things that could have affected your results. So one just again need to minimize that as much as possible. I mentioned SEL yesterday. This calculation is specific for the calibration set that you've used. So when you calculate this SEL with this equation would be for the validation set of your set of samples that you've used specifically. So again, just to indicate the reference methods contribute to the error, the spectra contributes to your error, the model itself sometimes contributes to the error, but sampling really contributes to a large error in your calibration. So it really needs a lot of attention. And I think I've covered most of this. Blending is really important when you grind samples, cleaning the grinder and storage. Mixing blending, especially when you work with powders, if it's not well mixed, the heavier particles will always settle at the bottom, and if you don't get a mix of that, your results would not be reliable. Then there are always tests that has some level of subjectivity, but even these tests people have tried with NIR spectroscopy, and it does seem to work. It's not necessarily as accurate, but it does seem to work. So for example, if you want to measure test on that's normally done with the farinograph or alveograph, which are tests that test the mixing properties of dough. So where with protein content, we actually measure the amount of protein present. With farinograph, alveograph measurements, if you want to measure the strength of the dough, now we measure a change in the protein molecule. So it's not just a straightforward presence of nitrogen. So it does become more complicated, but it has been shown that it can be done to a reasonable extent. So the reference method is important, and it is the Rosario showed the table of the information that you should include in your table. I wouldn't necessarily include this in the table, but it could be something useful when you discuss your error result, your RMSEP, to refer to the standard error of laboratory, which should be as similar as possible. It's seldom that you get it exactly as small, but it should be as similar as possible. Okay. I wonder if we shouldn't take a quick, would it be okay if we take a half an hour break now? And then I'll try and do the other two sets of slides in the next session. Shall we do that? We're now 15 minutes earlier, or I can continue for another 15 minutes. I need some indication. Shall I just continue for another 15 minutes? Anybody can say, or does somebody need an urgent cup of coffee? Okay, let me start with the other session. Okay, let's do, otherwise the second session might be too long. Let me just start with the next one, if I can just find it. Okay. Okay, so here I'm just going to spend a bit of time on, this is again, practical things that can affect the performance of your spectrophotometer. So I know it really looks like a huge amount of things that you need to take in consideration, but when you start working with your own commodity and you know your own commodity, only then will you be able to sort of decide which of all these factors would be applicable to my commodity. And that's the other thing I often say about NIR and including data analysis and chemometrics is when you do research with just some basic statistics, you can quite easily ask a statistician to assist with the statistics. He doesn't really need to know much about your product or your compound. You can just apply the statistics, you can use the statistics and explain it. When it comes to NIR, when you start doing chemometrics and analyzing your results, you really can only do it effectively if you know your commodity. So you cannot just ask somebody else, do this for me, and then hope you can apply it. So it's really important. A lot of the explanation you do with NIR results is because you know your product. I want to refer to the tables that Rosario mentioned towards the end of her presentation, where she showed the book and all these books with these long tables of where do absorbent bands, what absorbs at the different wavelengths. And it's only if you know your commodity, you need to know the composition of your commodity to also really interpret that effectively. So doing chemometrics, even if you don't do it yourself, you at least should be present to help the person doing it for you to interpret your chemometrics. Okay, so it's seldom that we find an error-free system. There are usually some sort of errors. If it's a huge error, huge mistake, we usually realize it, we figure it out, we can fix it. Small errors are not necessarily that easy to detect and to solve. So there are errors comes from the instrument, from the sample, from the operator. So when we look at NIR observations, we have, as we've seen yesterday, large data sets. We work with multivariate observations, which comprise of our data structure, but there's always some level of noise. And that noise can be systematic or it can just be random noise. And the systematic noise can typically come from our samples, instruments, operator. And we've just seen the errors that can be introduced by either samples or measurements or instruments from the instrument or the operator. So the errors that's induced by these parts of the instrument or the system, we really need to minimize that. Typhoon was asking me about stray light yesterday. So this is sort of instrument-induced errors. We cannot really change much about this. Stray light, I know he said he preferred to work in a dark room, which is not a bad idea, but stray light is really something that the manufacturers really try to minimize that. Rosario, I don't know if you want to comment on when you use instruments and stray light, whether it's okay to work in a room with light, whether one should really work in a dark room to prevent stray light if you're still around. Okay, I think Rosario might not be. Are you there?
Sorry, could you repeat, please, Marena?
No, I was just thinking, Typhoon was saying yesterday to try and prevent stray light. They tend to do their measurements in dark rooms, but the instruments, I believe that the instrument manufacturers try to reduce the possibility of stray light as much as possible in the instruments. So it shouldn't be an issue to use your instrument in a room with light.
Okay, no, yesterday I was talking about, for example, the linearity, especially the linearity and the loss of linearity in some cases. In our experience, we don't have problems with the stray light, But in some cases, for example, in analysis of some tissues, for example, the reflectance is too high. It's very, very, very high. So the signal is shutted. And we lost the linearity response of the signal regarding in the spectrum, regarding the concentration or the sample. So this is a problem. But when we are working with the PLS model, for example, we also evaluate the range of the linear response of the signal regarding the concentrations. I think that the coefficient of regression, it's a good parameter to find this relationship, if the range is okay, but it's important to report it, I think.
Okay.
But maybe looking for in the spectra, you can see if some sample has a loss of the stray light.
Yes.
So,
okay, so it can be checked, but I think the instrument manufacturers, they really try to minimize that as much as possible. And yeah, so the error can, to just about everything can introduce a small level of error. The instrument sensitivity to temperature, relative humidity, dust, vibration, that is important to take care of. So if your instrument is sitting somewhere where it's vibrating, then again, some of these instruments have to operate in facilities where it's really dusty. The relative humidity might not be ideal, so they should be tested and checked with the manufacturers that would be suitable to use them in such environments. And we've discussed the sample cell variants, where you use a range of cells to compensate for that to some extent. We find, in terms of the sample, that texture, location, where the sample comes from, which season, growth, if it's been stored for a period of time, all of this will affect your spectra. So what we need to do is, we cannot remove this. So if you calibrate, let's just, again, I'll just do wheat again. If you want to do a wheat calibration, we cannot develop a calibration each season for only this season, only this location. We really want a calibration that can measure samples irrespective of where they come from, when they were grown, what's the chemical composition, whether the texture is different. So this is really important when you start collecting samples to develop a calibration, is that you should include all of this variation. So you basically train your instrument by developing a calibration. You train your instrument to measure protein of a certain level, irrespective whether this from which location the sample comes from, irrespective from which season it comes from, irrespective of the rest of the composition of the kernel. So you really need to train your instrument to be able to measure protein in all of these samples. So we really try to incorporate all of this variation so that you eventually, if you want to measure a new sample, it doesn't really matter where it comes from, it will fit within your calibration. So a lot of these induced errors that we see is something that one should actually build into your calibration to reduce it so that it would not be an error anymore. The operator, the main thing with the operator is consistency. So we have to make sure that we do whatever we do as consistent as possible for each commodity. We obviously, calibration, development, wavelength optimization, pre-processing, transformation, all of that will be taken into consideration to try and develop the best model. But consistency in terms of using the instrument is important. General carelessness is something that just needs to be paid attention to. I find that if you have hundreds of samples to scan and you have to try and keep track, it's really easy. It's a tedious thing to do, but you just continue scanning. And I found that the minute when somebody walk in and start talking to you, you suddenly lost track. You cannot remember which was the last sample you scanned. Did you not by mistake emptied one sample into another sample. So it's a tedious job that you have to do, but so easy to get confused and do something wrong. So one needs to pay attention when you do this work. Instrument selection errors introduced by instrument. This is again, I would say the error that come in here is you have to select the right instrument for your application. So this is, you need to know what you want to do, how you want to measure it, in which form your product or your commodity would be, and select the best instrument for that commodity. So that would probably be one way of reducing unnecessary error from your instrument. I'm not going to go through this calculation. Phil really likes doing these calculations, so I sometimes for interest put them in. But what he tried to show here was that if your standard error of prediction was, in this case, 0.25, and he took a check cell and just scanned it over and over and over again and calculate the standard deviation. And using that information, he calculated that for this specific test that he did, the error of the sample presentation was 61% of the SEP. So 61% of the error of the SEP was due to sample presentation. So what he did here was, again, scanning the check sample in a more careful way. So he filled the sample, scan it, and not taking care how he filled it. So by reducing the standard deviation of those check samples that he scanned repeatedly, he could actually reduce the contribution of the sample error to the SEP. So this is probably not something that you will go and calculate all the time, but just to give you an indication that, and all this, the only thing that changed here was that the sample cell was not filled in a consistent manner each time. So again, it just comes down to consistency. In terms of instrument outputs, two things that maybe needs attention is you need to check the dust buildup and the cleaning of your dust filters, usually to the back of your instruments. Make sure that they are cleaned properly. Another thing that needs attention is the lamp. The lamp can reduce, as the halogen tungsten lamp, it can reduce its intensity over time. However, it can be used for a reasonable time. It usually has so many thousand hours that it can be used. We've used lamps for really long stretches of time. Companies where they really rely on accurate NIR measurements, they would quite easily replace a lamp on a regular basis. It can be quite expensive. Those lamps, I think they cost up to 10,000 Turkish lira, 10,000 rand per lamp. So it can be an expensive exercise, but if your company, if it's economically important for you to do accurate measurements, then it's important to look at the lamp and at least replace that. But apart from that, there's not much. I know there are some moving parts in instruments, but there's really not a lot that can go wrong in NIR instruments. Apart from here, if the internal cooling fan goes, that would be important, but I haven't really seen that happening much. Okay, diode array instruments. I haven't really, again, just what's important, temperature fluctuations within the instruments that might need to need attention. And again, here the instruments companies strive to minimize stray light. I just want to mention something else that could also happen. I've said now earlier, if you have samples that comes from different seasons, different locations, that you have to build that into your application. What also can happen is you might receive samples at different temperatures, and temperature definitely affects your NIR spectra. So if you develop calibrations and you want to test it on samples where the samples would arrive at potentially different temperatures, coming back to wheat again, in Canada, wheat can arrive at temperatures from -20 to 40. So if you really need to be able to calibrate all of those, then you have to include samples at -20, 20, -10, 30, 40. You really need to then cover that variation also in your calibration. Just something to remember. So anything that could be a variation in your specific sample, please take that in consideration and see if you should include that variation in your calibration. The composition of windows, just that, we've discussed that. I'm not going to go into that again. You might find that all instruments have internal standards. They might differ slightly. Normally the spectralons, but it shouldn't be too much. In the case of the near-infrared transmittance instruments, it's a bit easier. They just use air as a standard, so that's a bit easier to handle. Okay, diagnostics is said should be ideally run every morning or at least 2 or 3 times a week. So I can't say it enough. You must check the working of the instrument on a regular basis before you start analyzing samples. Sample errors. Okay, this is again, as I've mentioned earlier, I'm not going to spend much time on this. The samples could be, so sample errors, yeah. So again, texture, bulk density, different things can affect your sample. If it's important for your actual calibration, that variation should be included. Presence of foreign material, that's the same. So if wheat samples are typically scanned at silos before they are cleaned, then your calibration should be developed as such. If the samples are cleaned before they're scanned, then your calibration should have been prepared on clean samples. So this is just all, you just have to go through the whole process, understanding what you need to do before you start collecting samples, developing your samples. We've actually looked at texture, so the same here. The fact that you see this difference in these samples, if you want to measure hard and soft samples, you include all of this in your calibration. If you want to predict protein from both of these, then the fact that there's a difference doesn't really matter. You just have to include it in your calibration. Same with kernel texture. And it goes for all of this. If we take a sample from 10 locations, the same cultivar from 10 locations, you get variation. If you take one location, the same sample over 7 seasons, you will get that variation. So this is just to show we definitely get environmental effects, which we should take into consideration. Same with chemical. If you have such a high difference in moisture, for example, here we have maize samples with 54.5% moisture and a 12% moisture. Say you want to predict oil in these samples, this might be challenging. So to really have such a huge range in moisture might be challenging. So if you have these, if you want to analyze such a range of samples, you'll have to look at your calibration carefully at the accuracy of that. I'll just maybe show this and then we can maybe stop for now. This is again to show if you have really high, in this case, we could still measure the moisture, but in case this, the other one, this is chicken breasts. And we see here the chicken breast had really high moisture. So we saw as from about 1700 upwards, the detectors were saturated. So nothing were absorbed. So when you do a second derivative, you see here from 1819 upwards, pure noise. You won't be able to do anything from this part of the spectrum. So with high moisture samples can be challenging to analyze. Okay, let me do this one. This is then important. So if sample presentation is an important source of error. If it's really difficult to get that packing of your sample identical each time, then what one could sometimes do is, and I think the Buki instrument is almost set up like that. So when you scan something, they always scan triplicate scans. So you could then do a repack. So you scan your sample, throw it out, pack your sample, cell again, throw it out, pack it again. So to do repacks will also build in some variation, and then you need to average, you will then average those spectra. So you can also compensate for that variation to some extent. We've discussed okay, let me just check. Yeah, so whether it's NIR testing or whether it's reference testing, in both cases, we need efficient sample testing, and moisture loss is only applicable when you have to grind the sample. Then they have to make sure that we don't lose too much moisture or don't get heating during the sample. And this just shows that depending on the original sample content after grinding, how much moisture has been lost. So at high moisture, you can lose up to 3% moisture during the grinding process. And that means then that you don't actually measure, if you scan a whole grain sample and then grind it and measure moisture, then the reference moisture will not match your actual sample. So it's important to reduce that as much as possible. And maybe this is a good point to close. One of the rule of thumbs is if the conditions where you do your NIR measurements is comfortable, conditions are comfortable for the operator, it will probably be comfortable for the instrument too. So if you can handle the environment where you work, if you're comfortable in that environment, you can be pretty sure that your instrument would be comfortable and giving reliable results in that environment as well. Okay, so let's stop here for about half an hour or 25 minutes. Will it be okay if we start then at 12 again? So we'll see you back at 12. Thank you all for being here. And I haven't even asked if there's any questions, any comments from anybody. Please feel free to put up your hands, or those who are in the building, you can just come and speak to me. Feel free to do so. And thank you all again in Chile who got up early. I saw Hilmi also during the course of the morning appeared. So thank you all.
Thank you, Professor, for everything.
Hello, Hilmi. Yes, so we'll see you. What time? Okay, so it's back here 11. Okay, not 12. Sorry, I gave the wrong time. 11 time here. So 11 Turkish time. What time will it be you in
Chile? It'll be 4 a.m.
4 a.m. Okay, so 4 a.m. in Chile and 11 a.m. in Turkey. Okay, so we'll see you in about 20 minutes time. Thank you all.
Thank you.
Thank you.
Thank you.
Oh, Irene, I see you are also here this morning. Morning, Irene.
Morning, Prof. How are you?
Morning, I'm fine. It's good to see you.
Good to see you. Let me turn my camera.
Did you get the links yesterday?
Yes, I did.
You did? Oh,
Yes.
okay.
Yes.
Okay. I don't see Ariel here this morning. Are there anybody else? Is there anybody else here, Irene, from Kenya?
I saw Ariel. I don't know if he is.
Is Ariel? Did you saw Ariel here?
I did
Yes,
see
Prof.
him.
I'm here, Prof.
Where are you?
Wait.
Oh,
Show
there you
you
are.
myself.
Oh, there you are.
Yep. Actually, I'm in the lab. I'm following up. I'm doing some.
Okay. Multitasking.
Yeah, I'm multitasking actually.
Great.
Yes,
Okay.
yes, Prof.
Yeah, Irene's going well in Belgium.
Yes, yes.
Are you going home at some point, or will you be there for the next few months?
It's my last month, so I'll be going back on 28th.
No.
Yes.
When are you going back?
On 28th of this month.
Oh no, because I'm going to Belgium in August. I was hoping to see you.
Oh, so unfortunate.
Yeah, I was hoping to see you when I go back.
Mm,
Okay, so
Oh,
but
you
I'll catch up with you again, Irene. I'm glad you're
Okay.
here. I'm glad you're here. Okay, Ariel, I was looking for your name, Ariel, not your surname. That's why I've missed you. Okay, I'm glad you.
I'm there, Prof. I'm there.
Okay,
It's Buzera. My name is Ariel Buzera. So you can see
yes,
Buzera there.
I've got it now. Okay, I'll see you all back in a 15 minutes, 20 minutes. I'll see you in 20 minutes.
Okay, Prof.
Okay, keep well. We finished a bit late, so I'll just give a couple more minutes to make sure I have a few people before we start. I even got another copy. I have to. I can have from you, but I have both. Yes. Whichever you would like to have, if you like. I'll have everything. But more than one shot. That's my lunch. Okay. Okay, I think we probably might have a few people back. So if a couple can maybe just, somebody can just sort of put up a hand or call out a name so that I know I have some people back in the audience.
Yes, Marena.
Okay.
Thank you. Thank you.
So do I have Rosario?
Yes. Marena, may I ask you before your presentation now about the last presentation?
Yes, please.
A short question, just to ask you about the effect of the atmospheric moisture, the atmospheric humidity in the spectral acquisition. Do you suggest something special for the atmospheric humidity?
Yeah, when you said the relative humidity, or is that what you mean, the environment that you have your instrument in?
Yes.
I know just something, I can't remember who it was quite some time.
radila ili tako nešto, ona radi u Nexanu kao tehnolog. Kao neka osoba koja je, da kažem, kompetentna da ima, eto sada ne znam, to je ono bez promišljanja o tome. Šta vi kažete, šta vam više odgovara?
Okay, so Rosario, I think it happened.
Jesu, jedna i druga, jesu.
Just wonder, I think, right, Mila, your speaker is on. Your mic is on. Okay, let's try again. So I know it happens once when somebody had an instrument and they just couldn't get repeatable results. They kept on getting problems. And then they realized eventually that the instrument...
Pa može ona, mislim, ali ona je jedna druga, potpuno druga oblast.
There we go. Okay, now we can go. So Rosario was the instrument that they kept on getting problems with this instrument, and they eventually found that it was sitting underneath an air conditioning. And the moisture from the air conditioning really affected the instrument. So I think if you can have your instrument sort of in a reasonable relative humidity, room temperature, constant temperature would obviously be the best thing to do. Is that what you mean? The conditions where you keep the instrument or where you use the instrument?
Perfect, Marena, that's good.
Yeah, so I think, yeah, so one really try, that's what they said, sort of if it's comfortable for a person. So if it's high humidity environment, you probably will see some changes in your spectra. So that's likely to happen. There's actually so many things that one can still test so that one can actually illustrate it. Yeah, so now I'm just going to share a couple of slides here on does the calibration actually work. Rosario already spent quite some time on it yesterday. And something that I must admit, I haven't tried as much yet is that they find that if you still get that your calibration, your SCP, your SCCD, you still don't get a good calibration, is to actually just take your calibration and plot your calibration set self. So you basically plot the samples within that you've actually used to predict the calibration. And if some of those samples are real outliers, that would show. So this is at least the easy thing that one could do just to see if there are really potential extreme outliers. So when you do predictions, Rosario showed some examples yesterday as well. And although these first samples are sitting on the line, with biological samples, it's really seldom that we get something like this. We really usually get some sort of spread around the 45 degrees line. But you can get the nonlinear effect towards the end, the higher samples. You can get where the smaller percentage samples predict okay, but the higher percentage samples don't predict okay. You can have an outlier by extrapolation. So if you remove that outlier, the calibration might change completely. And then obviously you can have a bad outlier, and that is something that one needs to check. So it could potentially be that the reference method was just poorly done. So it might, in that case, it might mean that you just repeat the reference method, and then that sample will fit in your calibration again. So the one thing we always say is with outliers, you don't just randomly start removing outliers. You really usually try and explain why that sample would have been an outlier. If it was really a bad spectrum, if you can't repeat it to become better, then it's doesn't fit your calibration, then you have to remove it. If this one was a poor measurement, poor reference measurement, you can fix that and it should then fit your calibration. So it could be that your reference result for that poor one was of poor quality, but sometimes it is, and we don't really want to see it. Sometimes you just try an application which is just not suitable for NIRS, or suitable to use. We always want to try and make everything to work. Okay, so this is just still on outliers, and just another example. Here's like a really bad outlier. And if you remove that outlier, so you can see majority of the samples fit really well, just as one outlier resulted in a really large bias. And removing that outlier, you have a set of samples that fit well. And I just want to show you this. This is a set of samples that we did the other day. We had a calibration which was done on wheat samples from one country, and you can see the range was from about 9 to just under 14. And then we got hold of another set of samples which range from about 11 to 17. And we thought, let's just try and predict it. And this shows if your calibration samples was not included in your validation samples was not included in your original calibration, you will not be able to predict those samples. So there was a few samples that could be predicted, but the majority of the samples just did not fit this calibration at all. So there was just no way we could predict those samples. So what we then did, it's both wheat samples, it's from different countries, but then we combined the data. And when we combined the data, we got this spectra, and it was actually quite interesting. So the one benefit of this, and this is really more typical than what we would get in terms of the spread around the 45 degrees line. There is a slight, our 45 line is not really perfect. But the first thing we see is we had a much larger range of samples, and that often contributes to a better calibration. So here we now end up with, I think the RM-SEP was a 0.39, and it was for a small handheld miniature instrument, which was reasonably good for that instrument. But Rosario, what we saw for this set of data, the RM-SEP was really high. So we had a 0.87 RM-SECV, and the RM-SEP was 0.39. And this is something that we still need to look at, why we would have got such a high RM-SECV compared to the SEP. So we still need to look at this data and investigate this further. Okay, so just something about outliers. So if, say now we have all these outliers, these could potentially be all outliers on the set. But if we want to use these samples in future, then we have to include them. And this is what we did in the second slide. If it's an outlier that just does not fit your calibration and neither of your future samples will include such a sample, then you remove that as an outlier. Okay, and I just want to come back again. So accuracy is typically determined once, but precision is important. And we've said before that NIR might not always be as accurate as the reference method, but its precision is usually quite good. But it's also important, we want to always do these images where you can have good accuracy, poor precision, poor accuracy, good precision, or ideally you would like to have both. So it is important that when you always just get good precision, that you try at some point at least to get good accuracy as well. Because if you only have good precision with a bias, it will be costly for a company. I have a few slides here just showing samples in relation to each other when you plot them. But Rosario, you're going to do classification this afternoon. So I don't think I'm going to spend time on this showing the distribution of samples. So I'm going to skip these. I just want to show one more thing, which I always find interesting, is when we spoke about loadings yesterday, and Rosario had an interesting way of presenting the loadings where it was easier to see which wavelengths contribute to which cluster in the component plot. But if you plot your loadings as that it looks like a spectrum, although it really isn't a spectrum. This one, so this was a wheat sample. This is the first PC loading. It's upside down, but it's also because PCA sometimes is arbitrary, so it could be any way up or down. So what we often see with grain is that the first PC, the first loading typically looks like the grain spectrum. And that's an indication that the contribution is due to scattering. The second loading are typically moisture. So the second most contribution are usually because of moisture. And I don't have a third one. And the third loading are typically due to protein. And this is just something that we almost always see when you look at the loadings of a wheat sample. So it's really interesting. And then when you transform the data and when you, for example, say apply MSC, where you remove the majority of the scattering, then you find that your moisture then becomes your first loading because you remove the effect of the scattering your loadings all move one up. I always just find it interesting when I look at loadings of wheat samples. So I thought I'll just mention that. So if any of you work on wheat and you look at your PLS or PSA loadings, it would be interesting to see if you see the same. And the same with, this is just more loadings, which I'm not going to discuss any further. Just the last thing maybe is, one can sometimes, looking at the concept, the contribution of each loading. So we know now, if your R square is 0.6 to 8, the contribution of each of the different loadings to your actual model, depending on how many you include. Some software would provide you with the F value. And the larger the F value, the larger the contribution of your of each of the loadings. So if your software provides you with F values, it might be useful to also look at those F values. And I think that's all that I'm going to, and Rosario covered regression coefficients yesterday, where you can, from the regression coefficients, you can really see which peaks, in this case, water and starch, contribute to texture more than the oil peaks, which had a negative effect on texture. So I think that's all I'm going to show in this presentation. Maybe just to conclude, reproducibility, repeatability of reference method, important to determine. Reproducibility of your spectral data, you can just take the absorbances at 4 wavelengths and just repeat the spectra and calculate the standard deviation from those. If you want to see if NSRI is going to work, or NSR is going to work, NIRS is going to work for a new application, it's no use asking somebody. The best thing is just try it. So if you have the samples, you can just try it. And it sometimes seems like an easy technique, but it is time consuming. It does take a lot of work. It really takes painstaking work, and sometimes feels like boring, just scanning many, many samples. And also when you start with chemometrics and data analysis, I know you would do something and then your supervisor would say, oh, this looks really interesting. Why don't you try this? And then just once you've done something else, they think of something else and say, oh, why don't you try this? And I know even it's not as quick as just pressing a button and getting new results. It is time consuming to also do those data analysis, but in the end, it's always worth it. I just want to show you something I've found, what's his name? Typhoon's petri dish. So with the Buchi, you can do transflectance measurement. So typically you would just fill this petri dish with a sample and it's scanned from the bottom. So this is the transflectance cover, and it has tiny little feet, which is probably, I think this one looks like it might be 0.5 millimeters. If I look sort of the inside of these feet, it's like 0.5 millimeters high. So when you fill your container with a certain volume of liquid or honey, and you just put this on top of your petri dish, and you just have to make sure that there's no bubbles, then you inherently actually have a 1 millimeter path length. And this is much easier to handle than working with a real 1 millimeter quartz path length. So this is really easy way of scanning liquid samples. I thought I just want to show you that. Okay, so now I'm going to, oh, if I can just get out of this. Did I stop sharing? I just want to get my last presentation. I didn't want to open earlier. No. Am I still sharing? Okay, I'm just going to, it might be interesting if any of you, maybe we can just spend 5 minutes. if any of you have done some NIR work, it'll be interesting to hear what sort of applications have you tried. I'm sure in your group, Rosario, there will be some. Anybody? I unfortunately don't know. I only know of some people here. We spoke to Typhoon yesterday. If there's anybody who wants to maybe just share something in terms of what applications they've considered, to see if there's something interesting. Otherwise, I have to ask, did nobody do any applications? Rosario, in your team?
Yes, in my team, in our team, we work with lignocellulosic compounds and wood, especially wood.
Okay.
Yes. Wood,
Okay.
lignin, glucans analysis.
Okay.
And
so
also now the
yes?
detection of fungi using also microscopic techniques.
Okay.
But normally is forestry applications.
Okay, okay, that's interesting.
Also pharmaceutical.
Is there anybody else doing, Manley, quickly, what your application again?
Actually, Professor, we didn't work on NIR. We generally focused on ultraviolet region.
Yeah, you did.
For the sugar beetle.
Yeah, you did imaging, but you can still say it's still sort of NIR.
Oh, yeah. We were trying to find sugar contents of sugar beets. So we used hyperspectral imaging. It is between 400 nanometers to 1000 nanometers. So from 800 nanometers to 1000, we are actually kind of in NIR region. And we could get very beneficial information from that part. We are using halogen lamp. So for other fluorescence lamp just aren't enough, I guess, to provide that infrared region. So with halogen lamp, we could get good results.
Okay, so sugar content in sugar beet. Okay,
yeah.
I see Honey. Is Honey online? Honey? Yes. Are you there, Honey? Maybe you can just mention quickly what you've been doing.
Well, what I did is about putting aspirin tablets and see how much it degrades with bad storage conditions. And accordingly, we compared two types of tablets, and we made a calibration for that, for degrading aspirin to salicylic acid.
Yes. Yeah, and yeah, I spoke to Honey the day before yesterday. He used the tablet container for the buchi, and sort of they kept the samples at different relative humidities to see whether they get an increase in salicylic acid. And what happened was, unfortunately, one of his tablets is slightly larger than the opening that's allowed in the pill holder that's supplied with the instrument. So here, Honey is now sitting with the challenge: does he need to try and manufacture his own pill holders?
3D printing, probably. By 3D printing a similar plate to put these bigger tablets in it. We'll
yeah,
see.
so the difficulty, of course, that one tablet didn't result in good predictions. So the question is now, is it because of the positioning? So was it the sample presentation? And I know I've said so many times, sample presentation, sample presentation. So was it the sample presentation, or was it the sample composition, or was it whether it's compressed or not compressed? So he's got a few challenges there to solve. Anybody else that's done some NIR? I don't think. I hope more of you will hopefully start. If you can get hold of a small handheld, it's always worthwhile trying and starting. Okay, so I'm just going to go through a few applications. Again, I probably have more on agriculture than any others, so I might kind of skip some of those slides so we don't spend too much time on that. So near-infrared spectroscopy is really, it's used as a quality. I don't have an answer for that. Is there something else I can help with? Oh, sorry. This is my Siri. Siri Sammy speaking back. So it's typically used for quality control, and since it's used in the wheat industry, we still know about that. And because I'm mostly involved in the cereal industry, I'm aware of the application of NIR in the wheat industry. But I'm sure any of you who've done internships, I'm sure most of you would have come across an NIR working somewhere. But at the same time, I've heard so many times, and it brings me back to what Typhoon was saying yesterday, is when you just have to start doing it, it's really difficult. I've heard of so many companies, they heard of NIR, they realized that might be the solution, they purchase an NIR, and then it does not take long when people come and visit them again, the NIR is sitting on top of a shelf because they've just given up using it. So it is important when you have an NIR to put in the effort to start using it effectively. Okay, so it really is used in a range of applications. So just by speaking to a few people here, Yumi is doing sugar beets, a lot of woodwork. Arnie is looking at pharmaceuticals. There's a lot of work by actives. Typhoon is looking at ascorbic acid. Can you measure ascorbic acid? A huge range of applications. And I might just mention aquaphytomics right to the end. So food, bioactive, pharmaceuticals, it's used in petrochemicals, textiles, cosmetics, even medical applications. So there really are a huge number of applications. So since the cereal industry started within the food industry, it's really applied just about everywhere, and it's used to a great extent for food quality, but also for many other properties. So if maybe we just look at a few examples, is okay, obviously composition analysis, moisture protein is important. And in the cereal industry, apart from the flour mills, where it really plays a huge role is in breeding, wheat breeding. Wheat breeding, it takes 10, 12 years to breed a new sample or a new cultivar. And initially you have such small samples that you cannot really analyze it. So if you can now have calibrations that you can analyze that small sample, even just for protein moisture, and obviously we always talk about NIR as non-destructive. That means you can analyze your sample, you can get an indication of the protein content, and you can plant that exact sample again. So this is really useful in breeding programs where you now can, normally one could only start doing proper analysis in year 5 or 6 when you have enough samples. So with NIR and also now with the miniature devices where you can scan much smaller areas, this really becomes useful for the breeding companies. So it's a lot on breeding, so I'm not going to go too much in that. And again, so if you can calibrate for a range of commodities, so not just protein content, they could also then, at a very early stage, get information on the gluten strength and the potential of bread making properties. So the great thing, I think this is probably one of the main applications where non-destructive analysis is really important. We always say NIR is non-destructive, but in most cases we throw the sample away that we scan. We don't necessarily always keep the sample. So it is useful sometimes, or there are definitely cases where it's really non-destructive and the sample is either planted again or used for another analysis. Yes, so I'm not going to say much more on breeding because that's just very specific for breeding and the applications for that. So here again, you can, I just want to highlight this again. So different properties that could be measured. Color was good, kernel texture was good, Verino graph absorption because you measure moisture was good. But the minute when we started measuring development time, stability time, which relates to the dough development. So now you have to start measuring the change in the protein molecule and not the content as such. Then the predictions was not as good. Although it was reasonable, it was not as good as one would have liked it, but it could be useful at least for screening purposes. Yeah, so, and another Yeah, so because there are so many measurements that needs to be done when you analyze wheat samples, there are just a range of applications when it comes to that. And also certain classes, there's in the US and America, there's a lot of stress is put on specific classes and grades of wheat. In South Africa, for example, we don't have that many grades. We have 1, 2, and then a really poor grade. But where they have really a range of grades and a range of really strong cultivars, they also often need to do classification. And again, here are just a few more predictions. With a single measurement, it comes down to that again. A single measurement, you can measure a number of things, but again, falling number that's based on the presence of an enzyme, not easy to predict. Also, when you want to predict kernels that was damaged by a type of mold, also not that easy to predict. So when you start doing NIR, not all calibrations will work well. So we just have to keep that in mind as well. So you're not always going to get something that works perfectly. But you need to look at all your results to interpret that. Mixing, blending, I've discussed many times, so I'm not going to say more about that, the importance of checking that. Or maybe also what I want to mention here is the efficiency. Okay, two things, mixing samples and blending samples before you measure it, but actually also using NIR to measuring if you have to do blending in pharmaceutical industry. And that's, I want to mention the instrument again that I mentioned yesterday, the Harvey PAT instrument, which you can physically install in your blender. And as it blends, it will take spectra and measure, calculate standard deviation, and it will continuously calculate standard deviation until it gets a really low standard deviation that does not change anymore. Then you know you had the efficient blending. So that little instrument is really, really an efficient way of evaluating blending when you do blending in your samples. So here you can see this was just done manually. So when you measured something, standard deviation of an unblended sample, and after blending, how a huge reduction in the standard deviation of the same sample. So just measuring the standard deviation, a very efficient way to determine effectiveness of blending. That's still the same. Yeah, so flour millers, bakers, wheat intake, that is really places where NIR is used continuously. Maybe just to mention, there are actually, we said that NIR is the secondary method and we always use reference methods to calibrate, but there are actually a couple of NIR methods that has been approved by the American Association of Serial Chemists International as an official method. So near infrared ash method, I think the protein, and I think moisture. So there are some NIR methods that has been approved. Also, especially in terms of pharmaceuticals, I think, if I remember correctly, though, there's actually ISO code regulations, ISO documents, International Standardization Organization, where they have clear guidelines if you want to use NIR in the pharmaceutical industry, how you have to go about it. So then it's strictly controlled, because we can imagine how well pharmaceutical analysis must be controlled. So there are guidelines and documents to follow. And if you work in that field, you must please consider those documents. Okay, discriminant analysis. I know Rosario will cover that more this afternoon. So this is really not actual discriminant analysis. This is just principal components. So it's not models, it's just showing the distribution. And so if these are typical wheat samples, I know when you look at them like this now, they actually look quite different. But if they give them to you in a bunch, the wheat graders who are trained, they can tell you exactly which is which just by looking at the wrinkles. But most of us won't be able to just separate initially when we look at these. And then just scanning these samples, there is a clear distinction between, these were 3 red classes, I don't know which is which now, but there's a clear distinction between wheat kernels that actually look similar. So in the case of classification between Canadian, hard Canadian red wheats, it really is possible to distinguish between those samples. In this case, just purely on principal component analysis, but there are, Rosario, I'm sure will discuss other methods this afternoon, how to do an actual classification where you can get accuracy and prediction results. So, okay, these were white wheat classes, so discriminant analysis can be effective. Here they've classified between samples that were frost damaged or not damaged by frost. And I must say, this is often happens if you start to classify, and especially people, another popular area is at wheat adulteration or any food adulteration. You often get huge overlaps. So with NIR and food samples, you don't get clear clusters. So you don't, so again, you must not get disheartened by that. You just have to continue applying classification methods and try and find a mean to distinguish between them. Sprouting also was possible, different levels of sprouting to detect between the kernels. And these were kernels that were grown in different regions. So we just see the same cultivar, the effect of environment on the cultivars, which is can have a huge effect. So this just an illustration that you can do classification between some certain samples, whatever your need might be. Then I'm just going to show a few more applications without going into too much detail. This is meat analysis, NIRS used to a great extent on meat applications. And it's always, I've included the statistics here. If we just look at the RPD, if we measure content, like protein content, fat content, moisture content, you get RPDs of at least 5 or 9 or 7. So measuring the content of a compound, it can be done reasonably easy. One tricky thing with meat is sometimes really shiny and also wet, so it is at times difficult to measure, especially if you want to use a handheld instrument. We find difficulties because the shininess of the meat sample. When you start measuring technological parameters such as pH, color, water holding capacity, it can be done to some extent, but we can see the RPDs immediately decrease. So people would do it and report on it, but the accuracies are not as good as just measuring commodities. With fish, we found the same. Here I only have RMSECVs. And with fish analysis, we've started seeing that the handheld instrument is becoming more popular to use. So we get reasonable RMSEP, RMSECVs. Yumi, I want to ask you something quickly. Talking about RMSECV, RMSEP, you were saying when you started reading about NIR, in some papers, you only see RMSECV, and some you only see RMSEP.
Actually, I
right?
saw only RMSEP. They generally don't use the calibration one. They generally give just the prediction results. As far as I remember.
You only saw RMSEP.
I guess so. Yeah.
Yes, yeah. So he was saying, he was asking why doesn't he see RMSEP? And I was actually saying, and Rosario, I don't know if you might remember, many, many years ago, it was really interesting when people really just started publishing publications. It was completely acceptable for people to take a large sample set, just do a standard error of cross-validation and publish the results.
Yes,
So that was true. Yeah. And that was completely acceptable. But nowadays, unless you have an independent test set and sometimes validation and independent test set, you're not easily going to get a publication published.
Yes, no, it's very difficult.
Yeah.
It's necessary.
Yeah, but I think you were saying people mostly only record the RMSECP. I think it's useful to also include that, not necessarily the RMSEC, but also the RMSECV, because Rosario also said it's useful to know that those two values are close together. Then you know you have a reliable calibration. So it could be useful to include that as well. So the fact that I've now have the RMSEP/RMSECB was probably because the paper wasn't clear exactly which one they recorded. So fish is done to a great extent, again, moisture, fat-free fatty acids. They also look at some other defects in fish at times, and that is hyperspectral imaging is used to that sometimes. Fruit and vegetables can be tricky because it's high moisture content. And so the early applications was really just look at the dry matter of certain products and soluble solid content. So the soluble solid content was mostly determined with a reasonable low SEP, which could be done quite accurately. What I found was the acidity is difficult to measure in fruit. So when the water bands dominate, the concentrate of the acids is much lower than that of the sugars, but they found that they could measure the acidity because the indirect measurement of the acidity could be done because it correlates with the sugar. And that's what I said earlier also, that you could measure salt, sodium chloride, because of association with the moisture band. So also because of the correlation with the sugar, you could actually indirectly also measure acidity. So sometimes theoretically you should not be able to measure a commodity, but it could be possible. You also find that when you do fruit analysis, that a lot of the fruit work is done in lower wavelength ranges, because the lower you get, the penetration of the lower wavelength ranges are typically deeper than the penetration at the higher wavelength ranges. So you would often find that up to 1100 would be used for fruit applications due to that better penetration. Yeah, so sorting fruit, other measurements is stiffness, internal damage, sensory properties. People have really tried a wide range of applications. And this is probably one of the papers that's still mostly used is by Nikolai on, which they wrote on the application of NIR in fruit applications. I've actually included some references here. There's actually review papers written on just about every application. So if any of you are interested in this, please let me know. I can let you have the information. The dairy industry was initially mostly done on powders because it was a lot easier to work with a powder than working with other high moisture products. But nowadays they also analyze non-homogeneous products such as cheese, in which they can do dry matter. You can see a reasonable good RPD. And here you can see they've done sodium chloride, where they got an RPD of 2.9. It's not as good, but it's probably good enough just to use as a screening method to at least say yes or no, or completely out, or possibly okay. So they use the perturbations of the water signal in the case of the cheese, and that allows the sodium chloride to be predicted. And again, with cheese, they've tried all sorts, hardness, chewiness, creaminess. They did a range of sensory analysis, but as you can see, looking at the RPD values, for screening, we need at least a 3. For a good validation, calibration, we need a value of 5. So there's still a lot of improvement that could be done with these type of measurements. And similarly, some volatile compounds, again, here you see some higher RPDs, but still not suitable to use as good quality calibrations. milk is really difficult to work with, and there has been a couple of really good review papers written on milk in the Journal of Near-Infrared Spectroscopy. And this is because of the presence of the milk fat globules at the casein micelles in the suspension. So that really affects the scattering and the effective analysis of the samples. So milk powder is easy to work with, but the milk turbid liquid is not the easy commodity to analyze. In wine analysis, mostly bricks. Some try to follow the fermentation process. And another measurement, which I've probably been doing for quite some time, is the alcohol content. So alcohol's been measured in wine analysis. Actually, more work has been done on the actual grapes, where again, total soluble solids, and looking at anthocyanins, acidity again, probably in relation to sugars, and pH. Again, none of these apart from total soluble solids and total anthocyanins. RPDs not as great. Alcohol, reasonably easy with the RPD of 5.7, but the other commodities not as easy. Interesting here, they could, Gozzolini and his group could measure reducing sugars at quite a high level with the RPD of 10. So there's numerous applications, as you can see, can be tried, but I've seen already here, just being here at METU, where new applications is tried that hasn't been tried before. So there's always something new to do. And Gozzolini and Damsberg did a lot of work on grapes and wines, so there's a lot of references referring to those. In the case of beer analysis, it was more towards the characterization of the raw materials that got attention and determination of the barley properties than the beer as such. But so what they've looked at is genotype classification, and we also tried and do some work where we really try to determine or better understand the cultivars, the barley cultivars that would really work well in the brew house. Mycotoxin detection has received some attention in different measurements. It is difficult because it's present in such low volumes. It's like parts, we talk here about parts per billion, and NIR is not really good at measuring at such low levels. So what we sometimes see is that you actually pick up the fungus, but not necessarily the toxin. So it is tricky to measure at such low levels, but people still try to predict for mycotoxins. And intact analysis, moisture protein, always working well. Okay, then, our food adulteration. There's a lot of work done on food adulteration. This is, for example, adulteration of olive oil. That's one thing I came thinking of. Arabica and Robusta coffee was something that received a lot of attention. Jerry Downey was probably one of the first people who did a lot of work on food adulteration. And I, together with Vincent Botter, we wrote a book chapter on food adulteration. And it was really interesting when you read through all the publications that just about every paper finished with the word, this is a feasibility study. We need to extend the samples. It was really surprising to see that it's so difficult to get enough samples of adulterated samples that people can really say, this is a complete study. It is really difficult. We looked at adulteration of honeys. In the end, you can say, you can make a conclusion for your set of samples. It's really difficult to just say, okay, this is a complete study. This is what I'm saying. But adulteration has been an issue. there were melamine in milk powder. When something like that happens, everybody started immediately use NIR and see can they measure it or not. And there was huge problems with, I think, donkey meat and horse meat and beef meat, so the adulteration with different meat types. So adulteration studies are still receiving a lot of attention. Although it would be nice to see at some point an entire complete paper or complete study. Aquaphotomics, I must admit, is not really my forte, but it has received a lot of critique initially, but I believe that aquaphotomics can be used very effectively. So what they do is it relates water absorption patterns to the respective functions of the different biological systems. So it builds up a database of water absorption bands, that is water matrix coordinates, and then they identify certain characteristic patterns or certain water molecular structures that can be used for biological markers within certain complex biological systems. So it is a complex concept to understand, but I think if you have the right application and to apply it correctly, you can get really useful information from aquaphotomics. So in this case, they've plotted aquagrams and they've investigated different types of water. And by viewing these aquagrams in relation to certain wavelengths, I must admit I cannot explain this properly because I'm not familiar with aquaphotomics to a great extent, but you can tell that there's a difference between these waters where some associate more with wavelengths on this side and some more wavelengths on the other side of the aquagram. So it is an interesting application. So if you work with samples with high moisture content where this aquaphotomics could play a role, it might be worthwhile investigating. And where's her name now? Rumiana Tsenkova, she's the person that coined the term and really doing all majority of the work on aquaphotomics. So if you want to learn anything more about aquaphotomics or maybe apply it, Rumiana Tsenkova would be the best person to contact. Medical applications, again, something that I'm not as familiar with because I don't really apply it, but it really has the advantage that in medicine, it's really important. It has no side effects. You can just scan somebody's skin, can be used in real time. It's cost effective, it's portable. So I think the application in the medical field will definitely grow. Okay, pharmaceuticals is important. I think pharmaceuticals to some extent is, I don't want to say easier, but I think it is compared to other biological samples because they work with almost pure chemicals. And when you work with a pure chemical, the absorbance and the differences that you see, the classes you see within NIR is much more distinct. So it is useful, but because of the control, the way that pharmaceuticals the field needs to be controlled, there's much more effort that needs to go in to make sure that everything is well controlled, well tested. And again, coming back to blending, they do a lot of blending, but measuring blending is important, and also the measurement of particle size, which is useful. So medical pharmaceuticals, it's really, there are people only focusing on pharmaceutical applications, and it has a huge applicability in the pharmaceutical industry. Okay, then wool, also an interesting application. We actually currently at the department have a huge number of wool samples, and they're actually analyzing it quite complicated. I think HPLC at the moment, or UHPLC, and I think they plan to see if they can actually do some predictions with NIR as well. So to the degree in which air enter the wood follicle is something that's important, which they would like to measure. So wool has the opportunity to be investigated. And then, as Rosario is saying, they do mostly wood analysis, predicting lignin content, pulp yield, cellulose content, and probably other things. So wood is also receive a lot of attention. Roger Meader's done a lot of work on wood, and also you probably know them, Rosario, Anna Sandak, also doing a lot of woodwork, not just NIR, but other woodwork as well. And they actually just got a huge grant, and they built an amazing facility in Izola in Slovenia, where they've built this beautiful research facility, which is solely made out of wood, where they do all their wood research. I don't know if you know of that facility, Rosario. That might be interesting for you to visit. And yeah, unfortunately, I forgot his first name now. Schwanneger passed away a while back. He also did amazing work on wood. And again, Rosario showed that the books with the band assignments for NIR, and Schwanneger, he published a paper where all the band assignments specifically for wood. Rosario, I assume you might know about this. So this could be really useful, just the NIR band assignments specifically for wood. It was published in Journal of NIRS in 2011. Okay, soil analysis. It was difficult at time because soil contains minerals. Everybody wants to measure minerals. Theoretically, you cannot do it, but nowadays people claim that they can. So moisture has been done to some extent, and they've done some particle size, looked at particle size. They do try to predict some organic and mostly inorganic, and claim that they can do it to a reasonable accuracy. But not this, you see more work on soil, but not as much as yet. And then I think this is my last couple of slides, so we can maybe finish a bit earlier if there's, unless there's more questions, is precision agriculture. Nowadays, precision agriculture can be done with hyperspectral imaging. And, but in this case, what they do is they actually have a combine harvester. They have an NIR instrument that's attached to the combine harvester. So as they harvest, they actually measure the protein. So they know exactly what the protein content is at which part of the field as they harvest. So they can really draw up maps to say exactly what's the protein map, where do you get higher or lower protein content within your field of analysis. So precision farming is, again, they would have a conference on their own and spend a lot of time on finding means and ways to do this effectively. Okay, so we see within our analysis, we see a lot of feasibility studies. Everybody does a little bit of work saying it works, and then they always conclude we just need to add more samples. So we see a lot of that. So, but ideally, we really want to see large enough sample sets, well validated, so that you can say with a reasonable certainty that it's well, that your calibration work or not. What is happening more and more, and this is thanks to people like Professor Rosario and others, they keep on developing new chemometric algorithms or new multivariate data analysis algorithms that really help us to do more exciting NIR work. So instead of just using PLS and just check for a calibration, there are now other opportunities where you can start combining blocks of data, doing orthogonalization. You can combine blocks of data, doing exciting stuff. You can do ASCA, where you can really look at significant differences between effects when you analyze samples. So thanks to the development in chemometrics, it really gives us the opportunity to do much more exciting applications. Just something else, there's also, I can never remember what it stands for. EPO, external, I don't know, Rosario, if you can help me. EPO. So EPO is a technique that you can apply when you have external effects. So we had honey samples and we had effects of, say, location and something else, time, location, and or let's say location and time. And with EPO, you can somehow diminish those effects so that it does not affect your calibration. And we've really seen if you apply EPO as a transformation, you also get an improvement in your calibration. Okay, and then just on this here at the end, it's a review paper that I wrote quite some time ago. And this includes most of the applications that I've just discussed. And it actually also includes hyperspectral imaging. It's not often that people combine spectroscopy and hyperspectral imaging. Unfortunately, we didn't have time to touch on hyperspectral imaging today. I probably have time if you want to see something, but otherwise, yeah, so there's more in this review paper on applications and the use of NIR and also the application of hyperspectral imaging. Okay, I think this has become 2 long days, so maybe I should conclude here with the applications. And this gives you a slightly longer lunch today. Unless anybody wants to just discuss something, add something, any questions, or if they want me to discuss something else, maybe show you just some imaging results to give you an idea of imaging. I'm happy to do that if any of you would be interested to see that. Otherwise, we'll just have a proper lunch, especially those who started 2 o'clock this morning, can take a break. So I'm just checking if there's any questions.
Thank you, Marena.
Yes, Rosario.
Yes, Marena, and about your experience with fusarium detection, you can comment something else. We are working actually, but with fusarium circinatum. Martin Bravo is present now. Maybe he can comment something about his work. But for us, it's very interesting to know what is the experience in the detection of pathogens or microbiology applications, for example.
So who's working on Rosario? Is he here?
Yeah, no, Martin is here now. Martin?
Martin, where is Martin?
Martin Bravo.
Let's find him. Can I see him? Where is Martin?
Maybe he's sleeping.
Is it early morning for him? He's disappeared.
I don't know.
But he can maybe, when we start later, he can maybe say something.
Okay.
Because Dr. Phil Williams at our department, he still does a lot of work on fusarium. So he does mostly imaging work, but he does a lot of work, and I think he currently has students working on fusarium again. So I think NIR as well. So it might be interesting for you to discuss with him if you're interested. But if Martin can tell us later what he's been doing, then that will be interesting to hear.
Oh, Martin.
Martin, yeah, I can see his pictures here, but he's not here. We'll find him later.
Okay, we'll ask later.
Yeah, okay, but that will be interesting. I'll also mention to Paul Williams. I'm sure he'll be happy because it is sometimes tricky to get proper results or to get the results right, or just how to go about doing the analysis.
Okay, Marina, thank you.
Right, okay. Thank you all. So this was a slightly earlier stop today. So we'll be back at 2 o'clock. And we'll see you there. Thank you.
Hello again. Hello, Marina.
I just need to close the door. It's quite noisy next door. Hello, Rosario.
Hello. Are you the host, Marena?
Pardon?
Are you the host to share my screen?
Yes, you can continue. Yes, you can continue.
If I can.
Okay. Do I have?
Okay.
Do you
yes.
have? Okay, do you have permission to share? Yes, sure. Sorry. I think Eran or Zikru needs to give you permission to share.
It's okay. Just 1 second, please. Okay, I'm ready. With my clock. Okay, we can start, I think.
Yes, I think you can start, Rosario. Thank you. Looking forward to this. Thank you very much.
Thank you, Marena, and good afternoon to everybody, and good morning for the Chilean students. We will continue with the chemometrics part of the webinar, with the interpretation of calibration models, the description of some figures of merit that we didn't conclude yesterday, and then we will see some classification methods. We will finish in the last part with a description on other methods like curve resolution methods, okay? So I will take some slides from yesterday just to remind that you can estimate the diverse statistical parameters that we discussed today and yesterday too, but also it's possible to inform another analytical figures of merit in order to describe in a better analytical way the behavior of the models for predictions, okay? There's not too common report, for example, values of sensitivity or analytical sensitivity or detection limit, but in the last years, the calculus of these parameters is most commonly reported. So maybe you can see some alternatives you have in order to calculate these values. And these values are not only the analytical figures of merit of the analytical technique like NIR spectroscopy, but also includes the error coming from the modeling step and validation step. Of course, I mean, it's all the model, if not only of the analytical techniques. The errors are included from different sources of variations, including the development of the model. Okay. I go back to the slide from yesterday to talk about sensitivity, and you know that sensitivity is possible to be calculated using the vector of regression in case of PLS models, for example. But if you want to compare different models or different analytical techniques, you need to make a correction dividing the sensitivity by the spectral noise. This is very important because this is the analytical sensitivity. This is the parameter to be used for comparison of different analytical techniques, okay? And if you want to compare different models, you can do it with the same analytical technique. You can do it with all the parameters that we discussed yesterday. But for example, if you want to compare near-infrared spectroscopy results with another technique, for example, another optical spectroscopy techniques or chromatography results, you can use this analytical sensitivity rating, okay? And today I want to talk about limit of detection and limit of quantification. Why?
Sorry,
Because
Rosario,
Yeah.
sorry, can I just ask something quickly? I missed it. The previous slide, the sensitivity equation, this one. So sensitivity is the reciprocal of 1 over, is that the beta coefficient?
Yes, it's the inverse of the Euclidean norm of the coefficient of regression. Yes, that's true. But this value is related to the change of the signal regarding to the concentration for the unit of concentration. This is the concept of sensitivity. But
Okay.
if you want to compare this chain of the signal absorbance, and regarding the unit of concentration, you need to correct this value by the spectral noise of the analytical technique that you are using.
Okay, thank you. Sorry, thank you.
Okay. There are other possibilities to estimate the sensitivity too. The well-known method, including the net analytical signal, NAS, I don't know if you know this term, NAS, net analytical signal. This is a very common way, but mathematically it's similar to the inverse of the Euclidean norm of the regression vector. It's the same in the case for PLS. It could be varied regarding to other methods, other regression methods. Okay.
Thank you, yes.
Okay. For example, here we have in the selectivity estimation, we need this net analytical signal. In the case of CLS, it's possible to find this net analytical signal, but in the case of PLS or PCR, it's not possible. But now, in order to have an estimation of a quantification and detection limits, we need to define some source of errors in the predictions. And in regression methods, we are using this linear regression equation. And all the terms of this equation has associated one error on uncertainty, also in the slope and also in the Y or also in the X matrix. So it's normal to associate an error for each term of the equation, okay? So if we have a concentration in the case of inverse methods like PLS, we have the signal as X, and the Y is the concentration, remember. So we can estimate the error associated for the concentration, and this is the equation, and also the error coming from the signal. So concentration and signal will have associated an error if we can estimate this error using this long equation. It seems difficult, but it's not so difficult if you have just the mean of the signals and the mean of the concentrations in the calibration step. So, for example, if we want to find the error in the concentration of a new sample during the prediction step, you can use this equation using the uncertainty of the signal. I mean, if you want to calculate the error of the concentration, you need the error of the signal or the error of the spectra. And the spectra is very easy to find the error if you are using PLS method, for example, because you can substitute this equation by the residual values of the PLS model, for example, because you will have a residual in the PLS during the development of the model. You can take these values or these metrics of residuals and estimate this value, this error of the signals, and replace all this calculus or use these residuals in this second equation in order to find the error associated to the concentration in the prediction of a new sample, okay? But in theory, the error coming from three sources of errors here in this equation. The first one is the error in the signal of the sample, of the new sample used for prediction. The second one is the error coming from the calibration sample. So it's very important to introduce to this error the errors of the calibration samples too, okay? And then it's important to introduce to this equation also the error coming from the concentration of the calibration samples. So in summarizing, the error of the prediction is very, very affected by the calibration sample. Thank you. Okay. If you have this error associated to the concentration or to the prediction of the concentration of a new sample, you are ready to estimate the limit of detection and the quantification limit. But please consider that if you cannot to use this equation, log equation, because you don't have one term of this equation, for example, the leva, this is the leverage is the distance that your sample has regarding to the mean of each column in the X matrix. Very complicated, but it's not impossible to be estimated from the most of the chemometric software. It's easy to do it. But if you want to avoid this step, you can also use, if you are working with PLS models, to use the root mean square error of prediction. So you can use this value in order to have this error in the concentration, okay? But please take in mind that you need to know also the influence of the calibration samples errors in order to include these errors in the error of the prediction of a new sample. Okay, if we have this equation to estimate the error of a new sample, we can estimate the error of a blank sample because the limit of detection and the limit of quantification is calculated using a blank signal or blank concentration, okay? For a blank sample, you can do the same estimation with this equation. This is the variance, but you can calculate the standard deviation with a square root, and you can detect the error associated to the sample, which is significantly different to the concentration of either a sample with presence of the analyte of interest. I mean, you need to differentiate the signal and concentrations with the limit of detection at a very high interval of confidence, which differentiate the signal noise from the signal from the analyte of interest, okay? So you can use the standard deviation or error of the blank, and you can replace this value as is established by the UPAC, for example, and estimate the limit of detection, multiply 3.3 by this standard deviation. And this is the value, the long value, and you will find a limit of detection. But the limit of detection is not only an scalar. The limit of detection is also a range of scalar. I mean, the limit of detection is an interval of confidence where the sample concentration is different to the concentration between commons produced by noise. But it's not just one value, but also is a region with a limit of detection minimal and a limit of detection maximal. So the last publications include the range of limit of detection and not only one value for limit of detection. You can apply the same equations in order to estimate the limit of quantification, and you need to replace this value for 10. I have the calculus here. This is the equation exactly for quantification limit. And you will find now again a range of quantification limits, giving you information about the concentration of one sample with high statistical probability. For example, 95% of statistical probability to find the analyte with this concentration in your model of in your prediction model, for example, by PLS. Okay, it's not common to find the possibility to estimate directly from the software the limit of quantification and the limit of detection, but you can find in the most of the softwares the average values and probably the sensibility too, if you just need to divide one by the Euclidean norm of the regression of vectors. So this value is easy to be estimated. But if you don't want to do it, you need to use another software, and maybe this is a good software to estimate these parameters. This is the MVC1 software developed by the group of Professor Alejandro Olivieri from Universidad de Rosario in Argentina. So you can estimate also with different in a different way the error associated to the signal or to the concentration, and you can put these values estimated by different methods here, or if you don't put here values, the software will estimate the error of prediction, and also the residuals of the models, and the software will replace these values for these parameters, and will estimate all the parameters in order to have the quantification limit and the quantification or detection limit. Let me show you one example, for example, or in the quantification of some pharmaceutical formulation developed by Professor Castillo Lima from Universidad Federal de Rio Grande, who is using in last time this software too. And here we can see in the table not only the values of the error associated to calibration or cross-validation or prediction, the bias, but also the calculus of sensitivity. They calculate, I don't know how, selectivity, limit of detection, and limit of quantification. Different versions of MVC1 allows to calculate just one value or limit of detection or the range. In the last version, we can estimate a range with the limit of detection minimal and the limit of detection maximum. But you will see, if you are interested in this kind of calculus, then that the estimation of limit of detection, limit of quantification is done by sample. So you can see here in the equation, I go back, that you need the error in the signal and in the concentration of each sample here. So you need to estimate a detection limit for each sample. It's very rare because we usually report a limit of detection or limit of quantification for the model, but we can estimate now that concentration of the sample, of the unknown sample, and also
the header received, so he beat his ass. Well, in all fairness, Hayden provided.
Okay, thank you. And I want to conclude this part just talking about that the error of the calibration model is not the same. Please take care with that. It's not the same for all the samples. It's impossible to think that the error of the model will be the same at low concentrations and at high concentration. That's not true. We usually report the root mean standard error of prediction like an error of all the range that the model describes. But in practical terms, that's not possible. Maybe in low concentration, the error is higher. Maybe it's possible. It's common to see this behavior in univariate models too. So why not in multivariate calibration too? So the new researchers are focused in the estimation of the errors for each sample. Okay, that's new even for me, but I want to share this art of state now with you. So now I want to talk about.
Sorry,
Marena?
Lisa, I just want to double check what you've just said, which is now interesting. So you said normally we would have reported the RMSEP as the error, but are they now
on the range?
Yes. So how do they report it now? So if you say there's likely the error might be smaller for the lower values than the higher values, so how do they? Has some people now published on that somewhere? It's the first time that I heard that now. So I'm just
because the difference in limit of detection and quantification between samples, it's very, very small in most of cases. So if you have this behavior, you can measure or you can estimate a mean of limit of detection minimal and maximal of the range, and you can report this limit of detection rate. But if you have a model with samples absolutely different in concentration, and you estimate the limit of detection, the limit of detection and quantification are very different to the higher concentration samples, you can report it. But it's difficult to find this kind of report. In some cases, I see that, but in papers, it's not common. But the concept is very important, I think, because I think in some years, we will see some estimation according to the nature of each sample, or a group of samples, or regions of the calibration curve or rate.
Okay. So by determining the limit of detection for each sample, you get that impression that the RMSEP might not be the same across the entire range.
Yeah, and this is very important when you are using, for example, samples with very, very, very low concentrations.
Yes.
For example, we had an experience with the determination of antibiotics in food for fish. It's difficult to find or to use NIR spectroscopy by the sensitivity of the technique. So we need to report the limit of detection in this case, and the concentration was less than 0.5%. It's very, very low, but we need to demonstrate that our concentration is upper the limit of detection or quantification. So this is a challenge now. And the error, yes, and the error of the model, the root mean standard error of prediction, is too high for this concentration. It's at the limit, absolutely at the limit. So it's important to estimate, in this case, the error for this kind of sample at low concentration.
Yes, this is interesting. Thank you.
Okay. Now we were talking about comparison of methods or models too, because we can compare everything you want to compare here, just using a fit between the measuring concentration and predicted concentration. I included this method called AJCR, elliptical joint confidence region, that I will show you now. For the estimation of the accuracy and precision of the techniques. Because yesterday we were talking with Marena about the relevance to estimate the bias and also other parameters to define if the slope is really one in case you plot this measured versus predicted values of concentration after the application of your model, okay? How we can estimate this behavior, just plotting this fitting measured versus predicted values, and then apply a statistical method to estimate a region with under a confidence interval, for example, at
99 or 95% of confidence. And to drawing an ellipse, and this ellipse will be the region at a certain confidence level, and we will find the ideal point, 1 for slope and 0 for intercept, and we will see if this point is into this ellipse. Okay, this is the question for the ellipse. This method is elliptical joint confidence region, but this is the question of this is a function, mathematical function for ellipse, but it's make it or perform it under a confidence region, statistical confidence region, using the degrees of freedom regarding the confidence level that you want to estimate. Okay, but this equation can be changed if you are using data or comparing data heteroscedastic or homoscedastic. Marena today show us some examples of heteroscedastic data or homoscedastic. I don't remember the plot exactly, but you took this point, and it's very important to talk again of the variation of the error in concentration at different levels of the regression line. Okay, so if you have this variation, you will have the heteroscedastic data, and you need to change the equation for this kind of data. And if you have homoscedastic data and you assume that the error is similar to for all the range of calibration, you can use this equation exactly. Okay, so you can use this elliptical joint confidence region previously evaluating the behavior of your data regarding homoscedasticity or heteroscedasticity. Okay, and you can see some examples when the ideal point is into this region, this the ellipse, and outside of the ellipse. If you have this ideal point into the ellipse, your method is or has a very good accuracy. Okay, but if don't, like this example, the method is not accuracy. So you have bias, and you have values of slope and intercept statistically different to the expected ideal values. Okay, this is a very practical way to estimate accuracy and also precision, because the size of this ellipse is related to the precision of the method. Okay, here we have some examples of ellipses, and the ideal point is here, 1 of slope and 0 intercept. And you can see here, for example, this ellipse is green ellipse, and you can see that this method is accurate and also has a good precision because it's a small ellipse. And also have another model with less precision because the size of the ellipse is greater, but you can see that the method is accurate because the ideal point is into the ellipse. Okay, here we have 2 other models. This model, for example, has a good precision because the size of the ellipse is smaller, but it's not accurate because it's so far off the ideal point. And this model is the worst because it has a low precision by the size of the ellipse, and also is not accurate because the ideal point is so far. Okay, this is a visual evaluation of the accurate and precision of your models, or even if your methods are developed using different chemometric strategies, for example, PLS versus MCR-ALS, and you can compare the results regarding precision and accuracy with this method. Okay, and you can also estimate the error, the quadratic error, using this equation in order to estimate a quantitative value of the precision. okay? And you can also report with all the other figures of merit this error, root mean standard error. This is the name because you don't have here and a standard deviation because you are not using the -1 term here in the denominator, okay? This is a quantitative way to express the precision of the model. So this is a very practical strategy if you want to compare. I will back to the paper of Professor Castillo de Lima. Sorry. And you can see here how is the input to apply this kind of this tool. Sorry. You just need to have the predicted by NIR concentration and the reference values of the concentration. You just need to use the calibration if you want, but it's better to use the prediction in the external validation of data. This is better, okay? It's correct to use the validation set, data set. And you can compare, you can plot. If you have the standard deviation of each measurement, it's better because you can check if your data is or has an behavior heteroscedastic or homoscedastic behavior, okay? You can test that also with the same routine in MATLAB, call it EJCR, okay? But this is the input. The input could be only the concentration values or the concentration and the standard deviation of each measurement. This is important too, okay? To decide which equation to construct the ellipse will be needed. Okay. So with this example, I will finish the part of the estimation of the analytical figures of merit, and I will start another kind of chemometric methods used for infrared spectroscopy, near-infrared spectroscopy, as other optical spectroscopy, and many, many other analytical techniques, because these methods are very transversal for different applications. In this group of methods are called supervised pattern recognition methods or classification methods, and as the name says, the goal here is to classify the samples for different properties that we need to know what happens sometimes because the sample are groupings, but sometimes we just do need to classify and identify the class of one sample, for example, by brand or by origin or by species, etc. Okay? What kind of methods we have? A lot of kinds. There are classification methods too, but we have, or I show you here, a brief list of some methods. I will talk about briefly of another methods too then. For example, discriminant analysis or linear discriminant analysis, because there are different kinds of discriminant analysis too. And the K-nearest neighbor, this method is based on distances, the soft independent modeling class analogy, SIMCA, support vector machine or linear learner machine, among others methods used for classification, okay? We will see some of them, just some of them, but we will consider that these methods also can be classified according the goal and according the requirements of the population that they will investigate, or according to the classification of one sample, because some methods classify one sample in the classes that we supervise, and some methods just some methods are able to do not classify the sample to any of the classes that we supervise, okay? For example, The classification methods can be parametric or no parametric, depending of the distribution of data, of the population data, okay? For example, if the method is parametric, we will need a normal distribution of our data. If we don't have this kind of distribution, we cannot use the parametric methods based in normal distribution of data, okay? For example, SIMCA, Simple Independent Modeling Class Analogy, is a very good strategy to classify, but needs a normal distribution of data. And if we don't have a normal distribution of data, we need to apply some transformation of the data in order to have now this normal distribution, okay? But there are a lot of other techniques, especially in machine learning, that do not require normal distribution. Here I will show you the K-NIRS neighbor, and you will see that it's not a requirement to have this normal distribution. But the models or the methods for it can be also classified by the ability of discrimination. And if the model is able to belong to one sample to a single class, the method we call it discriminant. But there are methods like SIMCA, for example, where the samples can belong to one class, but the sample also belong to another class. So it's not limited to classify one sample in just one class, but the classification is possible in more to one class or even to any class. This is the powerful of SIMCA, for example. While methods like nearest neighbor or discriminant analysis needs necessarily belong just the sample to one class, to a single class, okay? And there also have another classification of these methods according the abilities to give us results under a statistical probability or not. If the method has a confidence or assign the class of a new sample with a confidence level, the method is probabilistic, like SIMCA, for example. But if the method just assign the sample to any class without a confidence level, the method is deterministic. KNN is a deterministic method, and SIMCA is a probabilistic method. I will take this linear analysis, linear discriminant analysis, in order to know if this method is good or not, because we don't discuss in deeper way this method today. But I just want to say you that this method requires normal distribution. And maybe this is the common error for analysts because this is a very, very used method, but needs normal distribution. And normally, people do not perform analysis, previous analysis in order to see the distribution of data. Just apply the discriminant analysis, and the method is based in a big equation of normal distribution. This is a Bayesian method. So the results are not so good because we are not applied before some strategies to transfer the population for a normal distribution of that, okay? Okay, what is the input in supervised pattern recognition method? We applied before principal component analysis. This is an unsupervised pattern recognition method, just exploratory analysis. And for PCA, we use we use just the X matrix with the NIR spectra for sample. But in this case, now in classification, we need a vector or a matrix containing the information about the class. Normally, we put a number for the class, and we can use, for example, if the first sample is from the class number 1, we will put just here 1, or here, if you have a matrix, we have some different classes, class 1, class 2, class 3, we will fill this matrix with 0 and 1s. 1s if the class is of the sample, and 0 and if the samples do not belong to this class, okay? So we can use this vector. It's most common to find software in chemometrics using the vector more than the matrix, okay? But you can do it depending on the software in both cases with anyone, okay? The steps are the same step that we described before for calibration models too. First step is the modeling or training. You need your modeling set, and this set requires the X matrix and the vector with classes, spectral matrix. And then you will validate the model using the validation step. This validation will be cross-validation, you know that, but also an external validation. And again, external validation is required nowadays, okay? And then you will find the equation for the classification. And we can use this equation for the next step, that is prediction. In the prediction, an unknown sample with a matrix with a spectra will be introduced to the model, to the equation of classification, and the output will be the class of this sample. It's the same, exactly the same. The difference is in the equation, because we don't want to have now, except in PLSDA, an equation of regression, not necessarily. There are different kinds to estimate the class in the prediction step, because equation can be different, okay? I will talk about each method then, but now I want to show you the common estimation of a response or parameters, statistical parameters, to evaluate if the validation of the modeling is okay or not. In the validation, we can evaluate the cross-validation and external validation with a matrix confusion like this matrix, this table, where the statistical parameters for classification are summarized. What we need to show after application of classification methods. First, we need to build a matrix. Sorry, I will take this one. We need to build a matrix containing the assigned class versus the real class. Okay, the real class, because this is a supervised method. So you know which is the class for each sample in the validation step. This table can be performed also for calibration samples, but it's not important to evaluate the statistical parameters in the calibration, but in the validation, because validation has a real behavior of data for future prediction and not calibration, okay? So after cross-validation or external validation, the confusion matrix is constructed with assigned and real classes, and the diagonal of this matrix will show us the correct number of samples classified by the model. For example, here, the real class, the one, has 22 samples, a total of 22 samples, and the model classified 20 samples as class 1, 2 samples as class 2, and 0 samples as class 3, sorry, okay? And 0 samples, this column depends on the method, because some methods has the ability do not assign to any class the samples, okay? But in this case, 0 samples were not assigned, so the total number is 22. But we can estimate here of a total of 22, how many % samples are well correctly expressed, okay? And this value is called normally non-error rate or percentage of correctly classified samples, okay? The same estimation can be performed for the second line of this matrix. In this case, from 22 samples, the 22 were classified of class 2, and the 22 has a real class 2. So this is a perfect classification. And in the third line, for example, we have, sorry, it's not 26, it's 22, 2, okay? And here have, for example, of these 22, 20 samples correctly classified as class 3, but one sample was classified as a class 1 sample, okay? This is the real class 3, but it was classified as class 1, okay? So this classification is wrong in this case. In one class is not assigned for any of classes. This is possible to obtain, for example, by SIMCA, okay? But other methods do not assign this classification, to not assign it to any of these classes, okay? We can estimate the percentage of correctly classified samples and report these errors are very important for classification. And these values also can be expressed like sensitivity and specificity, are absolutely different to the sensitivity that we reposed in the last slide for regression. It's different. The sensitivity is the percentage of sample correctly classified as a class I in this case. Is the percentage right of samples correctly classified. And the specificity is the percentage of samples from class different to the class I, for example, correctly classified as sample not belonging to the class I, okay? These terms are very used in diagnostic of some illness and medical application. It's normal to see some reports using these values or these names for evaluation of the successful of classification or diagnostic methods, okay? We don't have more statistical parameters for classification. I think this is the most important. There are a lot depending on the method, but the principal and commonly reported are the number of the samples correctly classified. And then, depending on the method, you can report another parameter, statistical parameters. For example, if you are using PLS for discrimination, PLS-DA, discriminant analysis, you can report also the parameters of the PLS. For example, the number of latent variables, the standard error of prediction, because it's possible to estimate it, and explained variance of the model, and all the statistical parameters coming from the PLS model, okay? So it depends of this method. But we can also find some qualitative information depending on the method, of the chemometric classification method used. So I will describe some methods, and we will see some other parameters, quantitative or qualitative parameters to evaluate if the model is good or not, okay? I will start by the K-NIRS neighbor. This method is based in the measurement of distances between the samples and the group of samples in a J-dimensional space. Okay, here we see a description plot, scatter plot of two variables. This is a space of two variables, but we, when use spectral data, have 100, 200, and 1,000 of parameters of variables. So the space is a J-dimensional. It's very, very big, okay? But how works the K-NIRS neighbor? Just to measure the Euclidean usually distance of one unknown sample. For example, this is the unknown sample X, and that distance is estimated regarding the nearest neighbor for each class. As supervised methods, it's possible know which sample belong to each class, because this is the information that we need in the vector of class, in the input of method. So we distinguish by colors here the class 1, 2, 3 for example, and for for the estimation of the class of an unknown sample, we will estimate the Euclidean distance for the first or nearest neighbor of each class. For example, this is the nearest neighbor for the blue class. This is the nearest neighbor for the green class. And this is the nearest neighbor for the yellow or orange class, okay? And we compare the distance, and the group which win this play is the group with a smaller distance, Euclidean distance. In this case, this. So this group has 1 vote, okay? And the model is constructed just using these distance estimations, okay? And then we can construct a table with the number of votes, and usually the first nearest neighbor is enough to estimate the class of one sample. In this method, we don't need to have a normal distribution of data as you see here. It's not necessary, okay? It's not required. So the KNN model has flexible boundaries like this kind of boundaries. But unfortunately, this method depends on number of samples. But it's necessary to have the same number or similar number of samples for each class, okay? But it's very practical and simple method to assign the class of an unknown sample. And this is a deterministic method. The sample will belong just to one class, not to more classes. In chain SIMCA, it's a modelative, parametric, and probabilistic method. So we need to check before the distribution of the data, and or in order to know if the data has a normal distribution, to apply SIMCA. SIMCA is constructed using the concept of the principal component analysis. So the matrix X as input is divided in different groups. The groups of samples are building considering that all the samples belong to the same group, okay? Samples are separated by groups, and then this sample set is submitted on an individual PCA. For example, here have 3 classes, okay? 3 classes, and each samples data set will be submitted to the PCA. And each PCA will have scores and loadings. Scores and loadings, scores and loadings. And the projection of the scores and on the PC1, PC2, and PC3 space will perform a box. And this box will have a probabilistic area or region with a maximal or a limit of variance, okay? Like a box, like a cloud. And this limit will estimate for each box, for each classes. For example, here is a box, here just need two principal components, it's a plane, and here is enough one principal component, it's not a box, it's a line, okay? But each distribution of data, box, plane, or different boxes or lines, has a limit of variance. If the sample is outside this limit of variance, the sample cannot be assigned to this class. But if the unknown sample is or has variance into the variance of each box or planes or lines, this sample belongs to this class. So there are many possibilities, because there are the possibilities to have overlapping regions, overlapping boxes, and if the unknown sample has variance into both boxes, belongs to both classes. This is a possibility to assign to one classes or more classes. one sample using SIMCA, okay? But also, if the variance of the sample, because we estimate a variance of the sample too, if the variance of the sample is outside the boxes of the planes or the lines of each classes, that sample is considered as outlier for these samples and is not assigned to any class. That's possible. And SIMCA gives us a possibility to see in a qualitative way if the sample is under these limits of the boxes. And this plot is called Commons plot. This is a Commons plot. And the Commons plot has the limits of variance for each class, like this figure. And we will see here, for example, the limit for the class 1, and here is the limit for the class 2. All the samples which values less than this limit value of variance, for example, all the samples in this area belong to, for example, the class, in this case, to the class 2. And all the samples before this line of the class 1 belong to the class 1 in this case, okay? This is the class 2, this is the region for class 2, and this is the region for class 1. But if the sample, like in this example, is only in this area, this is a only sample for the class 1 or 2, depending. But if the sample are here in this intersection place, the sample are not corresponding to or are corresponding to both classes. This is an overlapped region. The sample can be assigned to both classes, class 1 and class 2. And if the sample is here, the sample cannot belong to any of classes. This is the information that Commons plot gives us. For example, here, there exists a very, very good separation, and the variance is clear for each sample, for each group, sorry, but statistically, this sample and these samples are belonging to the same class, okay? There are not a statistical difference between these two groups. It's the same statistic, okay? And here, the separation is good because there are any sample in the overlapped zone, okay? And also, the dispersion of data is a measurement of the precision and accuracy of the method. If the variance is smaller, the dispersion will be smaller too, and the separation, the classification will be better, okay? And the SIMCA also estimate the distance between the classes, a distance between this class and this class. And if this distance is greater than 2, the model is acceptable or is good. But if not, the model needs to be improved, okay? This is another qualitative evaluation of the output that SIMCA gives us. Now we will see briefly, another method is PLSDA. What's mean PLSDA is the application combination of partial least square, the regression method, with discriminant analysis. PLSDA is useful when the number of variables, like in case of NIR data, is higher than the number of the samples available, okay? And if we have very, very correlated predictors or well-related. So we need to apply a reduction method like PCA, but PCA is not for quantification, but PLS is. And we use PLS as reduction of variables method, okay? The algorithm PLS, you know, the algorithm PLS is consisting in 3 steps: calibration, estimation of the regression of vector, and then validation or prediction step, okay? It's the same that we see or we saw yesterday. It's the same. Practically, we just need to change this Y matrix for the class vector. In order to have best response, you need to decide the limit to consider class 1 or class 2 or class 3 in your sample. And this is like a regression, but using values of classes. So it's very useful if you want to have perform to a classification using an increasing or some property, because it's very, very similar to a regression. But if you have, for example, a classification by use of percents or sense of different components, maybe the PLSDA will not be suitable for the analysis, and you need to apply another classification method. But if you have, for example, in our case, in our research, using PLS for estimation of the foliar damage in genotypes under cold stress conditions in plants, for example, we can decide, okay, the plants with higher stress, with low stress, one class low, class 2 is the mid values of stress, for example, of foliar damage, and the class 3 is the high damage, for example. We need to decide it. But the foliar damage is a quantitative response, okay? But if you have, for example, just different species, eucalyptus and pinus, for example, in forestry, and you can see, okay, how eucalyptus, globulus, eucalyptus, nitens, and pinus, 3 different species, and you don't have the certain that something increase the concentration among the 3 classes. It's complicated to apply this method, because there are other parameters that are not necessarily regressed, okay? So you need to apply this PLSDA if you have an answer that it's possible to be evaluated by regression, because the basis, the mathematical basis of the method is the regression, okay? You know what is the output in this method, PLS. You need to report the number of latent variables, the standard error prediction, the standard error of calibration, the standard error of cross-validation. You use also the cross-validation to select the number of the latent variables. It's the same, absolutely the same. The output path in this case will be the class of the predicted or unknown sample, okay? This is the output, just the class. And then when we find the class of each sample in the validation set, the matrix of confusion can be constructed, and the evaluation is the same. The estimation of the number or percentage of a sample correctly assigned, okay? So we added this table to the results obtained by PLS. Regarding other classification methods, there are a lot, but if the data is not linear, there are many methods without linear behavior regarding the concentration. Maybe the best strategy is the use of artificial neural networks methods with all the variants of this method. But in case of NIR spectra, normally linear methods are used, okay? We can try with artificial neural networks, but maybe the results will not overcome the results obtained by the linear methods. And another method very used lastly is the supervector machine. This method is a complicated method in terms of mathematics, but use an hyperplane to separate samples. This is the very simple concept. There are other methods of machine learning, like a random forest, which fits a number of decision tree classifiers from various subsamples of the data, and also the discriminant analysis like Bayesian method. But there are a problem that this discriminant analysis requires low number of variables. In case of a spectra, this is impossible, or you need to select 2 or 3 a wavelength and try to apply discriminant analysis. But the choice of this low number of variables is the challenge to use discriminant analysis, because it's not an easy way to estimate this variable or to select. It's different to the variable selection methods, because for discriminant analysis, you need at least or 2 and maybe 6 or 8, no more variables to select 8 or 6 wavelengths. It's very, very complicated from NIR. But we have some options. For example, if you are using PCA before, you can use the scores obtained by PCA before as original variables, introducing the scores values in place of the complete infrared data is better, and that discriminant analysis will run, okay? And another strategy is to use PLS. And if you have the scores but obtained by PLS, you can apply also discriminant analysis in place to use all the spectra. This is another option to apply this very simple analysis. Discriminant analysis is a very simple because it plots the same, practically the same, but here you have the function of discriminant function 1 and discriminant function 2. You will have an equation with coefficients giving which variable has more importance for the model. It's like a regression vector, but it's a short regression vector, just with a low number of coefficients because you are using low number of variables too, okay? So I don't know if you have questions about classification methods. I can show you.
Maybe I can ask Rosario, with your experience, did you find that, say, for certain applications, that some classification methods might work better than others? Because I remember many years ago, everybody was using SuChAQuality. SuChAQuality was the method to be used. And then soon after, one realized that SuChAQuality is not necessarily always giving the best results, so everybody moved to PLSDA. So especially for food applications, we used to see SuChAQuality a lot. But nowadays, I seldom see people using SuChAQuality.
Yes, SuChAQuality was the perfect method some years ago. That's true.
Yes.
But I think that it's by the possibility to have a probability to assign to a class. But this disadvantage has other methods too.
Yeah.
But now the classification tends to be simple, I think. Tries to use strategies do not require a lot of requirements like SuChAQuality. The normal distribution, for example.
Yes.
Support vector machine. I think support vector machine is now in the top of classification, I think. PLSDA works good in some cases, like you say that in food, identification, but in some cases, it doesn't. PLSDA is a little danger, I think, because if you are sure that the reason why it works, it's okay. If you have something that increasing in the different classes, it's good, it's perfect, it's simple, it's very simple. But in some cases, we don't have this increasing of properties.
But if you use support vector machines, what would be the least number of samples that you think one can use it on? Because I know it actually requires larger sample sets.
Yes, you can do it. You can do it. That's not problem. The problem of a support vector machine is that it's not a problem. It's not an advantage. Is the support vector machine combines nonlinear data with linear data. So if you want to complicate the problem using support vector machine, because it's not easy, it's good. But only if you have the requirement to use, because you have and behavior of data that you don't know. Is that really, really linear for all the samples or not?
Okay.
So perfect machine is the solution for this kind of data. I don't want to work assuming that the linear behavior of my data, and I don't want to use artificial neural networks because I know that I have a region with linear response too. I will use a mixture classification method like super vector machine.
Okay, okay.
This is the advantage, I think.
So that's worthwhile trying.
Yes, but Zinca is not using now like other years. No,
okay.
I think it's a super vector machine. Yes.
Yeah.
Next course will be about super vector machine.
Thank you, Rosario.
Okay, thank you, Marina. I want to show you some examples. For example, a table reported for the classification of some samples. These samples are samples of eucalyptus submitted to the stress in cold acclimatization in order to classify the genotypes by cold resistance. And this is the report, the number of correctly assigned sample. We have here 2 classes. In calibration and classification is also called by many authors by resubstitution. The resubstitution is the same of the calibration as well. I mean, if you want to see the successful of your prediction using the same samples of the calibration, you are resubstituting your model. Okay, this is the resubstitution step, is calibration. And then you can apply also the cross-validation and external validation. And here in this case, we use, for example, 3 external validation sets in order to check if the response is good, because we don't have a high number of samples. So we separate a first group, then belong to this group, and separate another samples, another group, and evaluate the model with external validation. And the results are very, very similar in some cases, okay? And then compare with some variants of the discriminant analysis. Please take that. This is the PLSDA, but using PLS scores and then discriminant analysis. But this discriminant analysis is linear discriminant analysis. But linear discriminant analysis is only suitable if you have the same size and variance of your classes. If you have, for example, this kind of classes, I go back here, this box, this line, and this plane. The distribution or the variance of the variance or of the variance of this line is the variance is very different to the variance of this group. And the variance of this group is different. And even if you have, for example, this plane in other position, like that, for example, linear discriminant analysis is not suitable for this kind of data, assumes that the variance of this sample, this group is the same of the variance of this group, and estimate a mean or an average of this variance to replace the variance of each group. But if the variance of the groups influenced by the number, for example, of samples too, could affect the estimation of this average variance. So linear discriminant analysis is not suitable if you have different distribution of each class. In this case, you have a solution is to use quadratic discriminant analysis or other kind of discriminant analysis. But you can take the variance before to apply this kind of method. By this reason, here, for example, I reported the values with a quadratic discriminant analysis. And in most of cases, the classification is improved with the use of quadratic discriminant analysis in comparison with just linear discriminant analysis. Okay, so there are a lot of possibilities to combine chemometric methods for classification too. Okay. Okay. You have more questions? Somebody? I don't know. It's okay. Because I have only now information about another method like MCRL
Can
resolution.
I ask a question? So,
Yes.
about external validation, how much should be, or how many samples should be in external validation? Like, for example, 10%, 20% of the number of samples we used in PLS should be used in external validation, or I don't know.
Oh, precision estimate. Yes, this table is only a report of the number or percentage of samples correctly assigned in the validation step. Yes, this is the report. And we don't have here in this table the estimation of the SEP, the ESSP, or the standard error cross validation. And we need to include that, but not in this table. This table is just to show the results of the classification as well. But you can include apart the parameters of the error of your model if you are using PLS, for example, apart. But this is only the confusion matrix. Yes, this is a problem because PLS DA, for example, has a lot of information as output because you need to select some parameters to perform PLS. But other methods, wow, artificial neural networks giving nothing, just layers and equations and giving anything else, no more. And SimCA gives you the possibility to estimate the precision using the variance of each classes. This is a very important factor, the variance of each classes, because you can compare the variance and you can see if you have two models, if one model has a smaller variance, this is better.
So if we have two models with different variants, it's better, you said?
In SimCA, yes. If you have different SimCA models, different, because SimCA gives you the variance of each classes and also a distance of classes. Interclass distance, it's called interclass distance, okay?
Okay.
And in this interclass distance, for example, there are some gold rules. For example, if the value is more than 2, the model is okay, it's good. But but you need to evaluate other parameters too. For example, the Commons plot. Okay, you can estimate also this variance and compare the variance because variance are related to the precision. Okay, in comparing in function of the interclass distance variance in Commons plot, which model is better? And to choose the best option there. Okay.
Thank you.
We can run a model like an example. I think we have some minutes and I will show you my screen. Please let me know if you see here a demo of pirouette.
Yes,
screen.
we can see it, Rosario, yes.
Okay, I will delete, not SimCA. Okay, I will try to perform SimCA, but I think this data has not classes. Let me see. Just for a demonstration, a simple demonstration, that this is very simple to perform. Returning to the regression models, okay? This is data obtained from a demo of pirouette chemometric software with the infrared data of different samples, hydrocarbons, gasoline, in order to estimate the octane content of the samples, okay? And here is the variable, dependent variable, in this case, the concentration of octane, and until here is the spectral data obtained by each 20 nanometers. Here, this is the interval. And this is the spectra. We can see the NIR spectra, and we can perform the method you want, okay? I will take here this option, run, and I will perform in an easy way a PLS, okay? You just need to choose the method, the chemometric method like PLS, and then you can select the pre-processing and the transformation methods. For example, I don't want to apply a transformation. I will not select here nothing, but I will use a pre-processing like mean center, and I will put here add and run. Okay, this is practically the raw data without transformation. And here I have the results of the model. Okay. The first thing that I need to evaluate is the variation of the standard error of cross validation regarding the number of latent variables. Here the program estimates using an F-test that the number adequate suitable for the prediction is 9. It's too high maybe, Marena, you can see that.
Yes.
Behavior, and maybe 4 is
yes.
enough.
That would probably be better.
Yes, you have here the error, decrease, and then decrease, but just a little. And even here, it's increased and then decrease again, okay? I will select 4. And when you select the number of latent variables, you can fit now the measurer versus the predictor values. Wow, this model is perfect. This data is easier, I think, to try to work, but in the real life, it's not so easy, but you can see here the if-it, and then you can see this data, but like a table, and you can see the output of the data. With 4 factors or 4 latent variables, you have here the variance, the cumulative variance of all the 4 latent variables. Here we have the root mean square of error of cross validation. SEP in this software is called SEP. And the regression coefficient of the validation, the error of the calibration. This is the error of the calibration. This is the regression coefficient of the calibration. We don't have the prediction because we didn't validate the model. Okay, I will try to do it, but now I will run another model, but including 1 transformation. For example, here, look at the spectra. It has not scattering problems, I think, but we can use, for example, normalization, okay? I will put normalization, add, run, and now we have another model, and I check again the number of latent variables in all this table in order to compare these results with the results of the first model, okay? I will check the factor select. 6 is suggested by the program, maybe 4, no, okay, I will put 4. In order to do not introduce noise to the system, I select this number as a latent variable. Then I will check the fit between measured and predicted values are okay. And we can check, for example, also the outlier. And here I have 2 statistical tests to detect outliers. This is the leverage, the first one. It's the same leverage used for estimation of limit of detection and quantification. And here we have the student residual. And this is the lines for the limit of the leverage. And this is the normal region for the second test, okay? If you have samples in this part or in this part, they are outliers. This is outlier, this is outlier, for example, okay? But I don't want to delete the samples because the effect seems to be good. But I will check the errors. Here I have the errors. And I will compare these errors with the first model. This is the second model for example, the SEP. The SEP is 0.31, and here the SEP is 0.25. This is best, okay? The regression coefficient, 0.9974, and here is less, okay? For example, in this comparison, I prefer to use this raw data. It's only with mean centering, okay? Normally, the pretreatment improves data, but it depends of your data. I can see here the data. There are not so light scattering. Maybe it's transmittance. In transmittance, the scattering is reduced, okay, compared with diffuse reflectance, for example. But it's easy to estimate that. And I can save the models, for example, here. Model Rosario. And I will use this model to validate the data. So I need an external validation because I did the cross validation here. When I put run, look at this window, ELS, here is the option of validation. And I selected before cross validation with the criterion of leave one out. Okay, so this is the model that I built. And then I will open my validation data set. We'll save. And I know that this data has an external data set to predict of 10. And this is the file, another file. And this is a validation data set, okay? And now I will open my model. Example, I don't remember the name, but this is my model. I don't know if this is the model. I don't remember where I saved my data, but this is a model, maybe of yesterday that I was working. And then I will predict. I made the predict. This is the validation external data set, and this is the model. And the model has this number of variables, samples, the range, the pre-processing, the number of latent variables, and so on. Now we put at, and the prediction was performed now. And then I check the error analysis. And here I have the standard error of prediction, or root mean standard error of prediction. It's very important that you check what equation use each software, because some software calls just SEP, but the equation is from root mean SEP, okay? And here we have the value, 0.21. And in the model, we have another value of cross-validation. This is a value of cross-validation. I have here the value of cross-validation with 4 latent variables is 0.31. And the SEP is 0.21. Okay, there are a little difference, but you can improve the results doing another pre-treatment of data in order to have more similar values, but it's okay. For the range, let me see the range of estimation between 84 and 94, almost 10 units, okay? And in 10 units, you have 0.2 and 0.3 of error. Thing is accepted, okay? And this is a way how works PLS model, and it's easy. The optimization is in the pre-treatment, especially in the selection of the number of latent variables, and then the prediction is very easy, and the analysis of error also, okay? If you want to estimate the figures of merit, limit of detection or limit of quantification, you need to apply the manual estimation or use MATLAB for your matrices and use the leverage and so on, okay? But this, and the classification is the same, but you just need, in this case, I will open again the samples. The first file. And in this sample, we have also a column with a dependent variable as class. This is the column of class, okay? All these samples belongs to the class number 1, and just some samples are coming from the class 2. Okay, 1, 2, 3, 4. There is a big difference between the number of classes. So it's not so good. We can test, for example, SIMCA, but we need more samples for the class 2, because SIMCA performs a PCA just with the samples from each class, in this case for the class 2, and we have only 1, 2, 3, 4. But we can try. Run. KNN is or requires, is very influenced by the number of the samples, so requires a similar number of samples. It's not mandatory, but it's better you have groups or classes with a similar number of samples, okay? We can test, for example, here the raw data with KNN. I will put run, and I will run also SIMCA apart, another model. Now I will run 2 models, KNN and SIMCA, okay? Probably SIMCA doesn't work. Oh, it's okay. Let me see here, because we have just 4 samples, so the maximal number of components, in this case in SIMCA, will be 4, okay? No more, because we don't have more samples. This is a KNN both matrix. Look at. With 1 nearest neighbor, what is the class for the first sample? Is 1. For the second sample is 1. For the third sample is 1. Okay? This is using the first neighbor, nearest neighbor. And this is using the second nearest neighbor. But normally, just with this neighbor, the decision is taken, okay? And it's not necessary to estimate the rest. But this is the confusion matrix, okay? This is a deterministic method. The sample is assigned to the class 1 or 2, no more. And the sample cannot be assigned to any class 2, because this is a parametric method, okay? And here we have 100% of the samples assigned to each class. It's perfect, okay? And this is the misclassification matrix, so the model was good. And regarding the question of Honey, I think, I don't remember, this is another parameter to evaluate, the class fit, for example, and you can see if the groups are very, very, very distanced between them, okay? And now we can see that one sample is very far, so it's groups, okay? And SIMCA has a lot of information. Look at very parameters with qualitative information. That's good for us. First, class projections. The class projection is the box. Is a cloud with statistical probability or variance limits of SIMCA classes. Okay, you can see here the classes are perfectly separated, and there are not overlapping of these clouds. That's perfect. Okay, but their samples are little far of the rest of the population. They are outliers. Look at. And then we have another plot with the class distance. In this class distance is a commons plot that I showed you in the paper, okay? Here we can see that the red samples coming to the class number 2 before they have values under this line. But in the case of the class 1, the brown sample are not belonging to the class 1 because has value greater than this line, okay? So the sample statistically correspond to other group. Here is just this sample, this group belongs to the class 1 because has values under the critical variance value, okay? Here we have 2 classes. So this group belongs to any class. It's a third class. And this is the advantage of SIMCA because KNN say just 1 or 2 and the classification is perfect. But with SIMCA, you can see that the class number 1 is divided in 2 classes. In one group of these classes correspond to another class, no class 1 and neither class 2, okay? And then you can see here also the interclass distances, okay? For E2, and do you remember that I mentioned that the value 2 is enough normally for separation of the classes? That separation is absolutely, okay, between these classes. And this is a probabilistic method, so it's possible to find maybe some values for probability to belong to each class. I don't know where. Let me see. No, we see only the best class for each sample. Yes, the best class is the class 1. In discriminant analysis or other software, we can see the probability too. It will be possible. Okay, but SIMCA has another qualitative information that is the discriminant power and the modeling power. It's like the regression vector for PLSDA. These plots will show us the influence of each variable for the separation of the samples or for the classification. Okay, the modeling power said as the if you use an independent variable, just one variable, each wavelength, I mean, and try to get the classification, you will have good results or not. For example, if you use this wavelength, you will have a modeling power next to 1. It means that this wavelength is very important and modulate alone very well the separation of classes. This wavelength 2, this wavelength 2, and this wavelength not, because has a small value, okay? And here we have the discriminant power. The discriminant power is the plot of the variables contributing more to the classification mathematical model. And in this case, for example, this part has very importance to classify the classes, okay? This is a qualitative information similar to the regression vector of the PLS that SIMCA give us. Okay, this is, I think. I don't know if you have more questions. I think we are on time for a break.
Yes.
And then continue with the, sorry, I lost my Zoom. Sorry.
No, we can still see you.
Okay.
You are still there. Okay, thank you. Thank you, Rosario. So if there are no immediate questions now from anybody, I don't see any hands, no questions, no comments. So shall we take, what time is it? If we do it, Rosario, you have to say, we can probably do a 20-minute break, or
Yes.
do you need half an hour?
I think it's right. For me, it's right. In 20 minutes. No
Yeah,
problem.
let's do a 20-minute break, and so we can start again. This is now 4 o'clock our time, so it's about what? Are you now at 9 already? Or what time are you at?
9.
9 o'clock. Yes. Okay. So we'll start Istanbul time 4 o'clock, and Chile 9 o'clock, and the others wherever you are in between. Okay. So we'll see you in 20 minutes. Thank you very much, Rosario. Thank you.
Okay. We'll start again with the last part of the training. Okay. I will share my screen. Okay. Now I will describe the last method, the last chemometric method. This is a method very used for resolution. Sorry, I don't know if I have my microphone open. Yes. Okay, this method is called multivariate curve resolution with alternate least squares. Okay, MCR with ALS. Okay, this is a combination of methods, but the goal of this kind of methods is, as the name says, the curve resolution. Okay, maybe this is a pre-treatment methods because we need to separate the signal coming from independent compounds in a mixture of signals obtained by NIR spectroscopy. Okay, this method is not only used for NIR spectroscopy; it's used also for other techniques, even not optical techniques, like, for example, chromatographic techniques. For example, electrochemistry methods to use these curve resolution strategies. But in this case, we will have a description of some cases where curve resolution is needed to define then a quantitative model or qualitative model for analysis of samples. Okay, this method, is very similar to the principal component analysis, and the objective is just to resolve the combination of signals that we have in a mixture of signals, and then you decide qualitative analysis or classification on either another chemometric strategy to analyze your data. Okay, this part is just curve resolution. Why is necessary to apply curve resolution methods? Because in NIR spectroscopy, as other methods do, the signal corresponding to the combination of very compounds present in the samples. Okay, if you are for example, analyzing foods, if you are analyzing soils or analyzing, for example, tissues, you have a lot of contribution of signal in a total signal or data. So we need to separate the signal in the individual contributions of signal of each component to decide what to do after the separation, okay? Now the notation is a little different of the PCA just to differentiate the composition of the X matrix, and the MCR-ALS method uses the D matrix. The D matrix is similar to the X matrix. It has M samples for N wavelengths, so it's very, very similar. Just the name change in order to do not confuse this method with PCA, okay? Then you can decompose this D matrix in two metrics similar to scores in loadings. Or more, it's the same algorithm. It's a singular value decomposition. In order to obtain two matrices, we'll call it a concentration, relative concentration matrix and pure spectral matrix or a spectral matrix, simply. It's not scores and loaded, but the difference will be later described. It's the application of some constraints to have a specific solution of this combination of relative concentration and spectral matrices, okay? Plus an error, and this is a residual, very similar. At this point, this method is very similar to the PCA. Okay, but why we need to differentiate this decomposition regarding to the PCA decomposition? The mathematically applied for this decomposition is exactly the same. Singular value decomposition, the name is distinct, but now we don't have a number, just a component, a principal component like P, because P is the number of components in an analogy with the PCA. But we need to define this value of P by PCA, but the solution or combination or solution, different solution of combination of C multiplied by transposed of the spectral matrix, it has different solutions, okay? This problem is called ambiguity, rotational ambiguity in this kind of decomposition. So the probability to find the best combination of C and S is difficult to get in a simple way, okay? So we restrict the solutions applying the constraints. What does mean constraints? The constraints are applied in order to have a solution with chemical meaningful. I mean, for example, the concentration matrix has not negative values because this is impossible in the real life. The same occurs with the spectra. You don't need to have a solution with a negative values for absorbance, for example, does not have sense. And the constraints is not only the restriction for the application of non-negativity, there are another constraints too, okay? But the main goal here is to differentiate this, the decomposition from the PCA applying these constraints to avoid solutions without chemical meaningful, okay? What happens in curve resolution, for example, after the decomposition? The decomposition of the matrix D by PCA will show you many options to find the combination of C and S matrices. And this step is regulated by the number of the components, the principal components you find in this step of decomposition, okay? PCA is very useful technique to find how many components your data sample has, okay? But these many components means that many chemical many components. So you need to remove before the random noise, the baseline shift, because if you didn't, you will find one component just for the baseline shift, or just for the noise, or just for the scattering. And so you need to remove that before, okay? You need to remove these effects in order to have solutions with components that could be the chemical, the real components present in your sample, okay? This is the first step, the decomposition, and you will find after the application of PCA the number of components. After the estimation of number of components, for example, 3, you will start an initial estimation of the alternating least squares process, giving to this equation one of these metrics as input. For example, you can choose C, and the software will choose the C values more different between all your data samples, and then will be estimate, if you have C and G, it will estimate the spectra matrix, okay? And with the predicted spectra matrix, we'll start again another iteration, and we calculate again with this spectra and this D value, another predicted C matrix, okay? And with this new C matrix, estimate again with the D, another predictor spectra matrix, and so on. This iteration is finished when the error of reconstruction of the matrix D is very, very low. And this parameter lack of fit is calculated comparing the residuals obtained after the decomposition of this matrix and the ALS iterations regarding the G original matrix, okay? When the lack of fit is very, very low and the next iteration has the same lack of fit, the iteration can be finished, okay? And on this part of this solution is ready to be submitted to the constraints, okay? And the constraints consist in to decide only in the solution that which have chemical meaningful. And after that, you can use the concentration profiles or the pure spectra for quantitative or qualitative information. I mean, if you have, for example, here as input the spectra matrix, you will find then after the iteration and after the finish of the iterations, you will find a concentration profiles. But this concentration is not a real concentration. This concentration is just a relative concentration. So you need to make a calibration curve or a regression model to estimate a real concentration. So you need now to apply a quantification method using the calibration set. If you have a calibration set, you know the concentration, the real concentration of this calibration set. And after the application of the convolution by MCR-ALS, you will have a relative concentration values, and you will develop a pseudo univariate calibration. What does it mean? All right, I will back here. This is the output of the MCR-ALS method, and this is the reference concentration or the real concentration. You need to perform a linear equation to relate this or both values for each sample, and you will find this equation just to estimate with this calibration the way to predict the concentration in a new sample. What does it mean that? It means that you have with these values the calibration step, and then or the validation step too, and then you will use this pseudo univariate regression line in order to determine the real concentration from the relative concentration given by the multivariate method. Okay, so this picture has more specific in details of the decomposition of the matrix D. What contains the matrix D? The matrix D contains the spectrum of mixtures. Okay, you don't need, as in the case of CLS, you don't need to have the pure spectra of each chemical component of the mixture. You just need to put here in this matrix the different mixture of spectra. Spectra for sample 1, spectra for sample 2, and this spectra has a combination of the signals of very, very components. You need to know how many components? No, you don't need to know how many components you have. This is the advantage of this method compared with CLS. You don't need to have the information of how many components you have, and you don't need to have the concentration of each component that you have in the mixture, okay? You just need the spectra. And then this spectra is the composite in C and S matrix, transposed of S matrix. And here, in the case of the C matrix, you will have as columns the number of compounds found by PCA. I mean, PCA is sublet on G, and PCA tell us how many components are in our samples, for sample 2 or 3, just looking for the cumulative variance explained by each component and the sum of each variance. And you can decide here how many columns will have this C. For example, if PCA gives us 3 components, we will have here 3 columns, okay? And the first column contains the relative concentration. It's not a real concentration, just relative concentration. It's like the scores values of the first component, chemical component, okay? And the second column, we have here the relative concentration for the second chemical compound. And the third column, we have the relative concentration for the third chemical compound. And the matrix, the transposed matrix S, we have as rows the pure spectrum of compounds. And that's good because the output of the method gives us the pure spectra of each component. And this is very useful for qualitative analysis of the mixture. I mean, the input is a mixture of signals, and in the output is just the contribution of individual signals to this mixture. Okay, this output can be interpreted, can be separated, can be used for classification or for direct interpretation or for other objectives that you have. Okay, but it contains the pure spectra of each compound. For example, if you have 3 components here as columns, you will have here 3 rows as corresponding to each chemical component, and you can plot these rows, and you will see the pure spectrum of each compound. Thank you. Then this matrix, C can be plotted column by column regarding the real concentration. For example, if we have here 3 components, we can choose just the first column and make or perform the pseudo-univariate calibration regarding the real concentration of this sample. If you are calibrating, you know these values. If you are using an external validation, you know these values of real concentration, and we perform this pseudo-univariate calibration, okay? Then you can apply the same parameters for estimation of the relative concentration in an unknown sample, and you will have this relative concentration, and using this regression equation of the pseudo-univariate calibration, you can determine the real concentration of the sample. And finally, this method of this curve resolution method give quantitative information about the concentration of the analyst of interest, okay? And you can see, or you can perform the same with the second column and with the third column to obtain the concentration of the second or third component, chemical component, okay? And this is the advantage of this method. Maybe some years ago, this curve resolution method was not used for NIR region, but it was very useful for mid-infrared region or other methods too, like chromatography, for example, coupled with the spectroscopy detector. But now in the field of the near-infrared spectroscopy, it's most commonly used, especially for a qualitative analysis of the pure spectrum, which is obtained as output. Okay, and that's all about this method, but since a mathematical point of view. But we can see together the application of this strategy, for example, in this paper of Roma Tauler, which is working many decades ago with these multivariate curve resolution methods, and has another or a lot of applications using this strategy for quantification too. Okay, I will check the application in this case of agricultural samples. Sorry, and I will show you the paper. This is a paper just to review how is the input and how is the output of this method and how is applying the quantitative analysis with this kind of method. Okay, for the case of the sample from agriculture, they used for samples of ray grasses and the spectra of the sample. Let me see here. This is the pharmaceutical application. But you can see here the spectra obtained of the mixtures for all the samples. If you see the spectra, you can see there are some problems with the scattering, so you need to apply the multiplicative scattering corrections or other techniques to solve that. But if you want to apply curve resolution method and obtain as output the pure spectrum of each component, you don't need to apply methods in the pretreatment step to modify the shape of the spectra. For example, if you are using first derivative or second derivative, the output will be also the second derivative or first derivative. And maybe it's better to avoid this kind of pretreatment, just to apply the methods of pretreatment will not affect the shape of the spectra. Okay, because if you have as output the second derivative or first derivative, you need also integration tools then in order to see the real or the predicted pure spectra of each component. Okay, and this is the spectra of the samples. The samples are grasses, so we have a lot of information. They have a lot of chemical compounds. You cannot know all the components that are contributing to this signal. That's impossible. So there are many properties could affect in more measure the signal and the spectra. Okay, which factors could be that? This is a question, and we don't know what compounds has the samples, but after the application of MCR-ALS, sorry, we are looking for this pure spectra as output, the S matrix as output show these compounds, 4 compounds. So PCA show 4 in this case, the presence of 4 sources of variation, 4 compounds, chemically meaningful compounds, and these compounds has associated an spectrum. This one, and this is the first profile founded by MCR-ALS, and this profile corresponds to high absorption of the water signals, so it can be identified like humidity contribution, okay? It passes also with the second component. You can see the profile, and after an evaluation of this profile, some bands corresponds to the protein contribution, and in the third compound case is also humidity. This is for the first system, and this is for the second system. The first system is just pharmaceutical, I think. So this is for the vegetable, the grasses, okay? Humidity and protein. But it's impossible to see the contribution of humidity and protein in the original or raw spectrum. But after this, the application of this method, you can see the individual contribution or the main contributors to the signal. Maybe it's possible to find another contribution, for example, a third contributor, but maybe it's just noise, maybe it's just baseline shift, so you need to improve the pretreatment until to obtain just profiles with chemical meaningful in order to identify which factor is affecting the spectra more, okay? And this is the qualitative information that could be obtained by this method, but also there are possibilities to find a concentration or estimation of humidity and proteins. The C matrix, the relative concentration matrix, can be evaluated or regressed using the real concentration of humidity in the calibration and validation set, and then establish an equation to relate these values, real values of humidity, for example, regarding to the predicted humidity, and the same case for the protein, and obtaining a spectrum and submitted to this spectrum to the convolution method, you can predict the content of protein and humidity of the samples, okay? When this method is better than PLS method, for example, when PLS cannot solve the overlapping of signals and PLS needs a high number of latent variables. For example, in this case, it's better separate the signal, and then the signal can be used by pseudo-univariate calibration for a quantitative application, okay? And maybe it doesn't work, and maybe the error of quantification by score resolution method is no better than the PLS. It's possible to, normally, PLS overcomes the results. Some cases, little cases, has best results after full resolution methods, and it depends of the kind of samples. It depends of the samples. It depends of the overlapping of signals. Okay, but this is the advantage of this method. You don't need to know how many components you have. And this is very important. You can find it using a PCA. But after the PCA, if you discover the pure spectrum of the compounds, you will need to perform a regression model, and you need to estimate, for example, in this case, the humidity of a calibration and validation set, and you did using a reference method, and you need also to estimate the protein content using a reference method for the calibration and the validation set, okay, in order to have this pseudo-univariate regression, because you need the reference values, okay? So that's all about the multivariate resolution methods. I don't know if you have some question, if you see the difference regarding the other methods used. The principles are absolutely different, absolutely different. This method use also reduction of variables because use PCA. Oh, okay, and I forgot. What kind of constraints we can use in this case? For example, is non-negativity in order to have result of C and S without negative values. but it's also possible to apply another kind of constraints like unimodality. Normally, unimodality is not suitable for infrared data because unimodality say that or assumes that the signal has just one maximum, one peak. And in spectroscopy, it's not normal that, but in chromatography, yes, we need just one peak of one compound, separated compound by chromatography. But in case of spectra, unimodality is not suitable. And another correlation constraint is a constraint very useful for quantification goals, but correlation constraint assumes that you have an interference percent in your data sample and you need to identify this interference in order to discard this interference to perform then the pseudo-univariate regression, okay? But it's very useful now, the correlation constraint. Okay. I don't know you have questions. It's difficult to me explain these mathematical methods, but I hope to give some parameters and some secrets to choose in a suitable way your chemometric method before the application. Okay.
Yeah, thank you, Rosario. I must say I've never tried multivariate curve resolution myself, and having listened to this again, I think it's something that one should definitely try at some point. So if I do, I will definitely get in touch, because although it was clearly explained, I think when to actually apply it is never that easy. So I will definitely, I think it would be worthwhile to try this to some applications. So thank you very much for covering this as well. Thank you.
Thank you to you.
So I don't know. Yes? Yeah.
Yes, I don't have anything else about the chemometric methods. I know that it's early too, but and I think that we described most of the commonly used methods. And if you want to know something more about, for example, this kind of method MCR, you can check this author, Roma Tauler. He is very famous for the application of MCR because this method has different application with different analytical techniques. Okay, it's very robust. We are trying now with Christian Fuentes to use this kind of method as pre-processing method in order to resolve some signals coming from RMI. So maybe it's possible, maybe not, but at the moment we have good results also with this kind of method for quality project.
Okay, yes, so if you don't have anything else, thank you very much, Rosario. I think they had a long couple of days, and I know the students here at Metro are they're still in between performing still some experiments before their holiday this next week. So they actually still got some work to do as well. So I don't think they mind if we finished a little bit earlier today. So thank you very much for your time as well for yesterday and today, and also everybody attending. I don't know if there's any further questions or comments. I've noticed that Erin again just asked for participation form to be completed. Imran, thank you from Imran. And also, what else did also, I think if there's anybody who wants anything specific to be covered maybe in future, please let us know. So if there's future training within the SuChAQuality project, then one knows what to cover, and if we can't do it ourselves, maybe to get somebody else to cover specific topics. Yeah, so if there's anything specific you would like to cover, please feel free to get in touch myself or Erin or Medjit or Rosario, and we can maybe organize something.
Yes.
Okay, is there anything else from your side, Rosario? Any questions, comments from anybody? But as I said, feel free to, if you don't want to speak now or say anything, please feel free to get in touch with us if necessary.
Thank you, Professor. Can we take a screenshot if anyone can open their camera?
Oh, do you want videos open? So if everybody can just open their cameras. Brush their hair.
Oh.
Make your hair tidy.
Let's
Tidy your hair. We've been busy all day, so it doesn't matter. They've seen us. Okay, who else is here? Rumbi, good to see you as well. Okay, you'll have to do 2 screenshots, Erin.
Okay, smile.
Okay, this is. Okay, and then we moved on to the next screen. I'll move on to the next one. There's another one. You still there, Erin? Can you do another one?
Okay, thank you.
Okay. Okay, thank you, everybody. It's also good to see your faces on screen at this time. Right, so thank you, everybody. It's 2 days just fly by again, so we appreciate you being here, and we're looking forward to see you somewhere soon, either with SuChAQuality meetings or any other platform. And yeah, so if any of you, I've also mentioned to Rasim, if any of you, I know many of you haven't started with your NIR project, so if you start doing NIR projects, feel free to get in touch with us if you need any help. That's part of the SuChAQuality project, so please feel free to get in touch with us. Okay, thank you, everybody, and I'll still see some of you around here and hopefully some of you on different platforms. Keep well. Thanks. Bye-bye, Rosario. Thank you for being here and your time.
Thank you to you, Marena.
Thank you. Bye-bye all. Bye-bye.
Thank you to the project too.
Yes, thank you. Bye.
Bye-bye.
Bye.